Good morning. Let me open our last plenary session. Today we are happy to meet one of our hosts here in Samara, Professor Pavelyev, who is a very well-known researcher both in diffractive optical elements design and application of such optics in different fields, including terahertz radiation. And so I hope that his presentation will be of great interest to the audience. Thank you.
Thank you. Good morning, dear colleagues. The title of my presentation is Control of Characteristics of High-Power Terahertz Laser Beams by Methods of Diffractive Optics. And it is devoted to using of diffractive microstructures for control of high-power terahertz laser beams. And the talk based on the results obtained in the frame of collaboration of some organizations. Experimental results been obtained in Novosibirsk, in Nuclear Institute, Butker Nuclear Institute. Design of elements been realized here, and elements which were realized by lithographical etching were realized in Samara University, and in General Physics Institute, new technologies for realization of diffractive microrelief for terahertz range have been realized. I will show it now. Here you can see electromagnetic spectrum, and you can see that terahertz range is placed in between electronics and photonics, between microwave electronics and photonics. So our idea was to bring methods of photonics to terahertz range. And to do, we had to bring or transfer our expertise from optical range, because before we had been worked in optical range, in visible and infrared range. We had to find proper materials, especially for high-power terahertz applications. And we had to develop technologies of microrelief structuring, of microrelief realization at the surface of these materials. Here you can see Novofel, Novosibirsk's free electron laser, which was used as source of high-power terahertz radiation in our work. It is placed in Novosibirsk, in Butker Institute of Nuclear Physics. You can see it here. And what is the motivation of research of this talk, or what is the motivation of research in terahertz range? There are some reasons. And one reason is specific feature of terahertz radiation. You know that terahertz radiation could be efficiently used for intrascopy, for terahertz spectroscopy, for soft ablation, for fundamental research, for another applications, for plasmonics, and so on. And of course, to do research in this field, to work with such applications, we would need sources, and also we would need elements capable to control characteristics of our laser beams: polarization state, intensity, phase, mode, content, and so on. Another reason is perspectives of using of terahertz radiation or terahertz technique for telecommunication applications, because you know that projects connected with 6G, connected with terahertz range, and last mile problem, and so on and so on. So again, to work efficiently for telecommunication, we would need elements capable to work efficiently with characteristics of terahertz radiation. And there is another reason, from my point of view, interesting reason to work in terahertz range, especially for us, because we came to terahertz range from optical range. This is an idea, or this is a reason connected with possibility to use such setup mega science setup like NovaFel as a base for physical modeling of interaction of electromagnetic wave with two-dimensional, three-dimensional sub-F-length structures with practically arbitrary topology. Because there are technological limits for fabrication of two-dimensional, three-dimensional sub-F-length structures. And you know that it's not too easy to realize experiment for investigation of interaction of electromagnetic wave with sub-F-length three-dimensional structure in optical range due to technological reasons. It could be expensive, but sometimes it could be nearly impossible because wavelength is too short. And in this regard, terahertz coherent sources are very interesting from the point of view of realization of physical modeling, because everybody of us use computer simulation, but computer simulation has own disadvantages because adequacy of model, convergence of algorithm, discretization, and so on. So physical modeling, if we have any material like silicon, for instance, with characteristics nearly the same in terahertz range and optical range, it would, we could use technology of structuring of such material, and then for experiment in terahertz range, for investigation of interaction of electromagnetic wave with a particular sub-F-length three-dimensional structure. And that's why it is interesting to demonstrate, or it's interesting to show, or important to show results, experimental results, which could be easily obtained in terahertz range, but it would be nearly impossible to realize in optical range, because you know that to realize, for instance, silicon or diamond nanostructure of arbitrary topology, it's not too easy. And of course, it's not too easy to make experiment, to realize experiment. So I will show such examples later. So plan of talk. At first, how to transfer our expertise from optical range to terahertz range. Regarding methods of design of diffractive optical elements, it was not too difficult because we used the same methods developed for optical diffractive optical elements. Optical methods developed for calculation of diffractive structures in the frame of scalar diffractive theory or in the frame of rigorous theory. So we used, in principle, the same approaches. We had to find proper materials and technologies. Especially it's important because we used high-power terahertz beams, and we needed substrate material stable for high-power radiation. And second, or third, realization of experiments typical for terahertz range, where we can show really advantages of experiment could be realized in terahertz range. So here some pictures illustrated different fields of application of terahertz beams. For instance, for terahertz LIDAR system, and in such system, of course, it would be important to have opportunity to control mode content of beams and orbital angular spectrum of beams, as well as polarization state. And a lot of papers devoted to using of terahertz laser radiation for scanning systems. And for such scanning systems, it's important to have opportunity to focus illuminated beam with elongated focus, for instance, for scanning of three-dimensional surface. So we have to think how to design element which could generate such elongated focus from illuminating beam. If we speak about such application like soft ablation or terahertz ablation, we have to think how to make element capable to form uniform intensity distribution at the surface of the surface to be structured by high power laser beam. So we have to develop instrumentation to do this, to control polarization, to control orbital angular spectrum, mode content, as well as intensity and phase. as a basement for development of such instrumentation, diffractive optics or diffractive optical elements could be used. And here I am showing very famous pictures, because first diffractive optical elements are well known for centuries, I think, Fresnel lens, for instance, or diffractive grating. But now we have a lot of different diffractive optical elements. For instance, now only a few diffractive optical elements could have classical analogs. Mainly, idea is to develop diffractive microrelief for solution of particular task without any refractive analog. But in each case, idea is the same. Idea is to find microrelief, changing the phase of illuminating beam in such a manner to get needed distribution of intensity or phase in scalar diffractive theory, or later we will consider another applications, for instance, for polarization state formation. So here you can see a very well-known picture, like we can start from classical lens, then we can use reducing of phase function of diffractive lens to zero, from 0 to 2 pi range, and then we can use quantization of microrelief to get opportunity to realize it by classical lithographical methods, because mainly diffractive optics started from microelectronics technology, for instance, from microlithography. Microlithography oriented to planar solutions, of course. But of course, to get high efficiency, and you could see it here, we are interested in either diffractive microrelief with a large number of quantization steps, with these steps, either in continuous microrelief to get high diffractive efficiency. So we've been interested in either multi-level diffractive microrelief, either in continuous relief, and then I will show how we try to solve this problem. Diffractive optics for terahertz range could be reflective or diffractive or transmissive. Reflective or transmissive. Of course, we can change phase in reflective mode or in transmissive mode. And here you can see a photo of reflective element designed by us for Novosibirsk group, and result to be published soon. You could see it here. And a silicon transmissive diffractive optical element. In principle, both approaches have own advantages and disadvantages, but I will be mainly concentrated on transmissive diffractive optical element in this talk. And it's interesting that for far terahertz range, for instance, for wavelengths close to 1 millimeter, it's possible to use for realization of reflective diffractive optical microrelief usual micromilling. We used simple micromilling setup we had at our department, not too expensive, and it works properly. So that's why this slide is more like joke, but partly, joke only partly, because we made such experiment. We realized cylindrical lens by cheap micromilling setup, and we found that for terahertz range, it's possible to make, yes, reflective lens with efficiency of 94% due to high wavelengths, which is really impossible to optical range, yes? But mainly we've been concentrated on transmissive mode due to advantages of such elements. And about stability to high power. Here you can see some photos made in Novosibirsk. They tried to use polymer solutions, terahertz diffractive optical elements made from polymer, but illuminating beam were power enough, and you could see the surface of polymer elements being burned by reflected beams. And that's why we had to look for more stable solutions, more stable material. So, and we used high resistivity float zone silicon. Here you can see a spectrum of transmission of such substrates. And you could see that such silicon have losses mainly connected with Fresnel reflection, absorption is neglectable, and we use such substrates for transmissive diffractive optics. As an approach, or as a technology for realization of binary, means two-level, microrelief at the surface of silicon, we used Bosch process, very well-known etching technology in our lab. And I told that number of levels are critical, is critical really for efficiency, for large number of applications. But there are still some application when binary elements is enough, when binary elements are sufficient. For instance, when researcher is not too interested in high efficiency, or if element is of such type where efficiency is not so important. I will show results of investigation of different binary elements. So here you can see very well-known scheme of very well-known lithography technology, and you could see in our setup. Yes, and you could see our very first result. We realized, of course, firstly lenses and diffractive gratings, and the quality was good because the characteristic size of microrelief was high enough. And then we realized anti-reflective coating of Parylene C material. And after anti-reflective coating, we got energy efficiency, not diffractive, but energy, honest efficiency, is very close to calculated one. So if you would interested in binary elements, it's not a problem to do it with characteristics very close to calculated ones. And here you can see gratings. So we got opportunity to realize different binary elements. It's very interesting, just a moment. It's very interesting that for realization of binary elements, it's not expensive really. Because for instance, as photomask, we used photomask with price of $2. Because we used high resolution printing, high resolution laser printers. And so for binary element, we could get photomask very easily. But if we would try to realize multi-level structuring, multi-level microrelief, we would need a number of photomasks, of course, not at the flexible substrate, and the price would be some hundreds of dollars. It's costly, and besides, procedure of realization of such high microrelief with large number of steps by lithography is costly and complicated enough. So there is another approach to decrease Fresnel losses. Fresnel losses are high enough. It's connected with higher optical density, and here you could see the anti-reflective structure is realized by the same approach, but we used two-time etching, and we used three-level anti-reflective structures. And you could see that using of such structures gave us opportunity to remove Fresnel losses at all newly. So the efficiency would be very high, but the question is how to combine sub-wavelength anti-reflective structures and diffractive microrelief in one process. So I will show some results obtained with binary optics when we can realize really binary elements. For instance, we realized focus eta element produced optical line along z-axis. You could see the intensity, and you could see the element, and binary microrelief of element was calculated by specially developed genetical algorithm in our lab. We optimized this binary microreliefs, and we are realized by our one-time etching. Another interesting application is forming of so-called diffraction-less beams. Diffraction-less beams means either unimodal beams, either multimodal beams consisted from modes with the same propagation constant. means such beams could be propagated in the free space without diffraction. And you could see here binary mask, and you could see here microrelief, you could see here the result of propagation of such beams. And this gave us opportunity to repeat our experiment realized in before for optical range, and demonstrating opportunity to use mode division multiplexing approach for enlarging information capacity of terahertz telecommunication lines. Here you can see model of such two-channel telecommunication system for terahertz range. So we could use two different modes. We can modulate differently these two modes, then we can combine it, and then after propagation in free space, we can use correlation filter to obtain information about signals in both channels. It was firstly realized in optical range a lot of years ago, and then we realized it for terahertz range because a lot of hopes connected with terahertz range using for telecommunication applications. Here you could see general scheme how we can use either different modes, either different orbital angular momentum for enlarging of information capacity of telecommunication system for here for optical range, but it could be done for terahertz range also. And here you can see, yes. Could we see film now?
Mm-hmm.
Uh-huh.
Mm-hmm.
Could we see a movie now?
Mhm.
Yes? Okay. So, yes, here it could be seen. You can see the model of two-channel terahertz telecommunication line, and you could see like Dr. Choparova closing one channel, and in this case you could see correlation peak corresponding to presence of signal in one channel, and then she is closing another channel, and you could see zero in the center of correlation peak. So it's in terahertz range, it's looking much more better than in optical range because there is no practically there is no noise. Here you could see it. So the same approach could be used for terahertz telecommunication lines. And the same approach was used for generating of rotating or beams for terahertz range, or so-called beams with pre-given orbital angular momentum. And here you could see elements we realized, and you could see generated intensity distribution, very close to calculated one, of course, and you could see general idea of these rotating beams, how the phase changing in the cross-section of such beams. Very well-known things. And here you can see results obtained by Professor Knyazev group for investigation of phase structure in the cross-section of such beams by use of interferometry. It's really beams with pre-given orbital angular momentum. Such investigation has certain availability for applications because a lot of papers been devoted to so-called self-healing of rotating beams or beams with orbital angular momentum during propagation in non-uniform media. And it's important for LIDAR or remote sensing systems because there is a very important feature of such beams to restore structure in the cross-section after passing through uniform media. It sounds a bit magic, but the physics is very simple there because high order modes are diffracting much more faster, and as a result, after passing through uniform media, after propagation in free space, we could see the amplitude phase structure very close to the structure of initial beam. here you can see the picture from this paper, and here you can see results obtained by us for self-healing of terahertz beams with orbital angular momentum. You could see that just after this noise, or after passing through this non-uniform film, you could see that the structure is destroyed nearly. But after moving of camera after this film, you could see that structure would be better and better and much more close to initial beam structure. Another application of binary optics, especially it's important really for long wave applications, are subwavelength binary elements, for instance, calculated in the frame of electromagnetic theory, for instance, for control of polarization state in the cross-section of beams. And here you can see a result of a photo of our subwavelength silicon oxycon. And it's very well known from rigorous theory that such elements could convert linear polarized illuminating beams, coherent beams, to coherent beams of, with cylindrical polarization of second order. And it was done, and it was investigated. You could see the setup with polarizer and analyzer, and you could see that it's really, it was really polarized in proper manner. And then this idea have been developed, and in the frame of rigorous theory, such elements, wavelength elements, have been calculated or have been designed for producing of beams with such complicated polarization structure. You could see these pictures, and then it was investigated in Novosibirsk. You could see here microrelief we obtained, and it was easy enough to obtain such binary relief again, because it's binary structure, one-time etching, and very cheap photo mask, so it was not so difficult. But if you would try to realize this experiment in optical range, it would be very expensive, because you would need to realize subwavelength photo mask with real aperture, with full-size aperture. And then it was again investigated by use of setup developed by Professor Knyazov, and here you could see that rotation of image after polarization, after analyzer, was in the same manner like it was predicted. It was in good agreement with results of computer simulation. Again, about quantization level number. Of course, binary elements could be used for such applications where 2 levels of microrelief is sufficient. But of course, for focusing, especially for focusing of high power beams, we would need high energy efficiency, and to do this, we would need especially technology for realization of continuous like microrelief. Here you can see the same picture, yes. And we had solving this task together with group of Professor Konov from General Physics Institute, because they have a lot of experience for laser ablation structuring of such materials like silicon and especially diamond. And our first, yesterday there was a talk of Dr. Kamlynuk from this group, so I will not touch in details these results, but I want only to demonstrate results, what is really important for us, like for specialists in diffractive optics. First result was realized, first result was when lens with 4-level microrelief was realized by laser ablation. And here you could see results, and here you can see that diffractive efficiency was a bit only a bit smaller than calculated one for 4-level diffractive lens. Then group from General Physics Institute improved the technology, and here you can see the result of realization of lens with continuous like microrelief with really good quality, and you could see here a result of focusing by this cylindrical lens, and you could see that efficiency is quite good here. And then there was idea to use such promising material like diamond diamond films for making elements of terahertz optics. And here you could see transmissive spectrum of diamond, and you could see that for far infrared and for terahertz wavelengths, it could be done. And here I placed very old results obtained in before for 10.6 microns, when elements for 10.6 microns were realized in General Physics Institute by laser ablation. And a group from General Physics Institute developed two different technologies. Here you can see technology of realization of continuous-like microrelief at the surface of synthetic diamond by they did it in two stages. At first, they realized microrelief at the surface of silicon. Then they deposited diamond layer on the surface of microrelief, and then they removed silicon. And they received diamond cylindrical lens. Here you can see how it works. It works quite good. And then, yesterday, Dr. Koblinov demonstrated this result, and I want to demonstrate it again. They used black diamond, synthetical black diamond, for realization of elements with continuous-like microrelief or microrelief with high number of steps with high quality. And you could see that results of formation of pre-given distribution in the focal plane is very good, and it's very good agreement with calculated or predicted results. Yes. And in beginning, I told that appearance of coherent terahertz lasers, coherent terahertz sources of radiation, and appearance of diffractive optical elements or instrumentation for changing of the phase structure of orbital angular momentum spectrum and so on, giving opportunity to realize experiment which would be very difficult or nearly impossible to realize in optical range. For instance, here I want to mention results connected with so-called quasi-Talbot effect for Bessel beams, with orbital angular momentum. And experimentally, by a group of Professor Knyazhev, it was shown first time experimentally that if you would use in Talbot scheme beam with orbital angular momentum instead plane wave, we will get repeating of these pictures again with the same special frequency like in Talbot effect, but we would have a race of rings with the same, with orbital angular momentum of each ring corresponding to orbital angular momentum of illuminating beams. It would be difficult to realize such experiment for optical range, but it was realized after it was realized in terahertz range, because so it was first experimentally demonstrated. And here you could see the movie, how intensity distribution is changing for this array of beams of, with orbital angular momentum when the camera is moving along the text. You could see it here, and it's very interesting to see competition between different beams here. Yes. And another example how appearance of terahertz coherent sources and development of instrumentation for the control of parameters of terahertz radiation can be used for getting of completely new results. And this result was again obtained in Novosibirsk. First time it was demonstrated that it would be possible to excite different rotating surface plasmon polaritons at the surface of cylinder, and then it could be seen when they're coming from cylinder, and again we can use the same idea with mole division multiplexing, so it's possible to realize multi-channel telecommunication line based on plasmon polariton, so it was realized that this is a cylinder of nearly 10 centimeters. So, of course, in optical range, specialists in plasmonics could comment it, but for optical range it would be nearly impossible to do it. So, and of course, such relatively large wavelengths of terahertz radiation giving us opportunity to do easily enough not only such planar two-dimensional elements like diffractive optical elements, but as well three-dimensional metamaterials, photonic crystals, and so on. It's interesting that three-dimensional printing could be used for realization of photonic crystals and photonic quasi-crystals. That's very well-known formulas. And we used, yes, it was calculated, it was simulated, of course. And then we used three-dimensional printing for printing of such polymer matrix with holes. And these holes have been filled by wood alloy, which has relatively small temperature of melting. And as a result, we realized two-dimensional and three-dimensional quasi-photonic crystal structures. Here you could see it for wavelengths close to between 800 microns, I guess, and 1 millimeters. And it was investigated, and a result of spectrometry was close to result of simulation for, you know that, for instance, to realize three-dimensional quasi-photonic crystals in silicon, it would be difficult because to use lithography, but lithography is oriented for planar structures in principle, and so you would need a lot of etching, and so for Terahertz range it's much more easy, but there are interesting applications for do this. So in conclusion, I can say that diffractive optical elements and diffractive structure of terahertz range giving us opportunity to control different characteristics, including for terahertz beams, including high power applications, and for telecommunication, for soft ablation, for gas charge, and so on. We could use such elements, and besides, it could be very interesting, I think, lab for investigation of interaction of coherent electromagnetic wave with different topology three-dimensional structures. And so we have to solve problems connected with features of diffractive optical elements further. So thank you.
Thank you very much for your very interesting presentation. It is open for discussion, questions, please. Yep.
Okay, thank you very much for a very interesting talk. My question is concerned with the possibility to apply your optics not for monochromatic terahertz wave, for time domain, when the pulse is pulsed radiation, when we have quite wide range. In this case, the Fourier transforms on your elements are quite difficult because. Do you have an experiment on this way?
There is another. Maybe it was to. I understand question, but maybe it was to use another approach based on free-form elements without diffractive microrelief. Because for terahertz range, am I right that it's not high-power application? Yes. It is not necessarily high power.
Not high power, of
yes.
course.
Yes, and for not high power application and for not coherent and not monochromatic light, maybe it was to use free-form elements, because free-form elements could be easily done by three-dimensional printing, for instance, or by micromilling, it would be, from technological point of view, I think more adequate. But it could be done, of course. For this particular application you mentioned not, but you remember this slide with joke about garage? I will show you. Beginning. Just a moment. Oh, this one, yes? This was our first attempt to make a freeform element. It was idea to test it with cylindrical lens. But the quality was good enough even in the case when we used very cheap old micromilling system at our department. So we can do more complicated freeform element either by three-dimensional printing, because resolution of printer is of 20 microns, newly 20 microns, is we can use micromilling and we can do it, I think.
Thank you.
Okay, very interesting talk, thank you.
Thank you.
You showed us very interesting phenomena like Bessel beams association with topological charge, which can be also demonstrated in optical range.
Yes.
Are any interesting phenomena in terahertz range which are principally impossible in optical range?
If we speak about free space, I think equations are the same. But for instance, for plasmonics, as I know, for plasmonics there is a serious difference. And I think Dr. Gerasimov will be giving talk especially devoted to this. And if we would use diffractive optics in different waves with different intensity phase distribution for plasmonics, there could be very interesting results.
Other questions? I have a minor question. You demonstrated mostly laboratory prototypes. Is there any industrial production of diffractive optical elements in our country?
Regarding our country, yes, we had we had some orders from commercial company from St. Petersburg, and we did it. But diffractive optical elements mainly oriented, of course, to coherent applications, and most of commercial applications, of course, connected with not non-monochromatic line. So they use, for instance, polymer lenses if it's not high power, and so on. But we realized some projects.
Probably for 5-6 generation power could be quite high.
Yeah, yeah. But in each case, there was such interest, and we realized some orders for diffractive optical elements.
Other questions? Then thank you again.
Thank you.
And now, please proceed to the favorite topics of your own. We have 4 halls ready to receive you. Welcome.
Hello, dear colleagues, good morning. So we are starting our morning session of laser matter interaction. And the first talk is given by Professor Mayorova from Lebedev Physics Institute, Samara branch. So the talk is entitled Structured Optothermal Traps. Please, Professor Mayorova.
Good morning, everybody. Dear colleagues, I'd like to present our research, Structured Optothermal Traps. The study was carried out at Samara branch of Lebedev Physical Institute. And single beam optical traps or laser tweezers proposed by Ertl Erskine more than 30 years ago have found their application in biological, chemical, medical, and biophysical research and in other fields. And if you use the structured light fields with complex distribution of intensity or phase light fields with angular momentum, you essentially expand the functional capabilities of laser tweezers. 2 years ago, Dr. Porfiryev told us about bottle light fields. Today we listen about Bessel structured light fields, and this is one more example of structured light fields, so-called spiral beams. These beams was proposed by my colleagues from Samara branch of Lebedev Institute, Dr. Evgeny Abramechkin and Dr. Vladimir Volosnikov many years ago, and these beams have complex and very different intensity distributions. They have complex phase distributions and they have angular momentum, non-zero angular momentum. And due to angular momentum, the optical tweezers on the base of spiral beams as on the base of other structured beams some capabilities. You can transport microscopic objects along trajectory by trajectory of intensity distribution. You can see it in clip. You can rotate assembles of microscopic objects and you can impose different deformations. But the vortex optical tweezers and the point optical tweezers have some limitations, and they are relatively high laser power. The photon and thermal damage for some objects, and the requirement of refractive index contrast between target objects and surrounding solution. And this limitation can be overcome by optothermal traps. There is growing interest to optothermal traps last time. In optothermal traps, sharp focused laser beam used not only to create optical power, but also to create a gradient of temperature and to create a thermal convection flows. And micro and nano objects are captured and transferred by liquid flows in optothermal traps. And so you can use small powers, you can capture macro objects from large distance, you can capture objects of various geometry, of various morphology. It can be transport objects and also absorbing micro objects or sub-micro objects. And also you can organize areas of increased concentration and microparticles and clean areas. And in our study, we want to combine the capabilities and advantages of vortex optical tweezers and optothermal traps. And we want to implement structured optothermal trap and to demonstrate its capabilities and features. You can see the scheme of structured or vortex optothermal trap. We used the laser with the wavelength of 0.53 micrometers, and the output power varied from 2 milliwatt to about 40 milliwatt, and to generate complex vortex light fields and vortex optical tweezer, we used liquid crystal spatial light modulator. And to realize optothermal tweezer, we used an absorbing light filter as the bottom of a cell with micro objects or sub-micro objects. And in our experiments, it was a glass orange color filter. The cell has cylindrical shape, and we conduct our experiments with latex microparticles of different diameters and with silver microparticles of submicron size, and also the use yeast cells. In this slide you can see the calculated phase mask, and this calculated mask allows us to generate intensity distribution in the focal plane of different shapes, in the shape of square, in the shape of triangular, and also in the shape of double counter and the lattices of zeros. And this is the technique of generating of such phase masks, and we used the optics of spiral beams and the Gertzberg-Sexton iterative algorithm. This is the mathematical model of our optothermal trap. We use heat transfer equation for the liquid layer and the light absorbing substrate, and we also solved the stationary Navier-Stokes equation. And this is some results at beginning for annular optothermal trap. You can see temperature distribution and the flow velocity depending on R. And can you clip video? Must be. No, I want to demonstrate that particles move rather quickly to the light ring from distant reading, and that they began due to angular momentum to move along the ring trajectory. And when we want to compare the velocity of movement of particles in optothermal trap and in optical trap, флешка там был, там все хорошо было. The velocity depends on laser power, and it depends on the topological charge of vortex lexicon. You can see that the velocity of particle movement around annular in an optothermal trap is higher than in polyoptical trap for all values of laser power and topological charge. And we also want to check what determines the motion of particles along intensity distribution, for example, along Archimedes spiral in optothermal trap. The angular momentum or the intensity distribution. Does the spiral create addition swirling of the liquid? And to answer these questions in a special way, we calculated the phase mask so that the phase twist was opposite, but this phase mask creates the identical intensities. And in this clip, you can see that particle move in the spiral due to transfer of orbital moment. Because you can see the change of the motion detection of lattice sphere with the load of the phase distribution with direct and invert place on spatial rate modulator. And the particle change the direction of movement despite the fact that the twist of the spiral does not change. Here the frames from the video that illustrating the capabilities of a structured thermo-optical traps to create specified configurations of micro and sub-microparticles. You can see the different shapes of intensity distribution. You can see that the particles of various sizes were captured, and it is interesting that we realize the optothermal in the shape of double contour. And we propose the technique for fixing the captured microparticles on substrate. We add serum albumin to our solution, and then we short time increase the laser radiation power, and in resulted the captured microparticles or captured nanoparticles were fixed on the substrate due to coagulation of the albumin caused by local rise in the temperature of the solution. And the laser power required to fix the particle depends on the concentration of albumin, and you can see that the higher the concentration, the lower power of laser radiation at which the particles were fixed at the light boundary need. And in these frames, you can see the particles fixed on substrate. We have the trap in the shape of triangle. Microparticles were captured and aligned along boundary, and then we short time increasing the power, and in resulted the microparticles were fixed, and then we rotated the triangle or moved the cell relative to the light beam, or in some of the clips we turned the phase mask and then moved our sample, and then the procedure was repeated. And similar experiments were performed while changing the configuration from one shape to another, from ring to square. And the particles remained fixed on the substrate for a long time. They could not be washed by running water, and they do not dissolve in the aqueous solution. And here you can see the dynamic control of structured optothermal traps. In left movie, you can see the captured microparticles, and we move the line. And in right movie, you can see the rechange of configuration from square to triangle. Optothermal traps have some disadvantage. It's not always good that all particles transfer to maximum intensity. But if you need to turn off our trap, microparticles will begin to leave the trap due to Brownian motion. And the other disadvantage that when working with microparticles of biological origin, they may be demated by a thermal effect. And to avoid this disadvantage, they proposed the scheme of complex optothermal trap, the optothermal trap on two wavelengths. It's, in fact, we have a point head trap and an optical vortex trap. The scheme is presented in the slide, and the advantage of this scheme in comparison with a simple optothermal trap is the ability to stop the movement of particles, to be reducing of power or turning off one of the laser. And this is the base result. Optothermal traps of complex configurations, including double loops, lattices of zero, and tunable configurations of various shapes, were created for the first time. The possibilities and features of structured optothermal traps for capturing and moving particles and effective grouping them in fixed configurations were demonstrated. And a simple and effective fix of fixing captured micro-objects on a substrate along the boundaries of light traps was proposed using an serum albumin and a short-term increase of the power of the laser radiation. Thank you for your attention.
Thank you very much, Professor Mayorova, for a very interesting talk and the perfect timing. So it looks really like magic. If anybody wants to ask the presenting author.
Thank you for your talk. My question is it possible to fix on, for example, plastic substrate, plasmonic nanoparticles like nanostars and nanospheres with average diameter about ranging from 20 to, for example, 100 nanometers? We are working with such objects.
We work with nanometers about, of the size about 20 nanometers. We work with such nanoparticles, but it were silver nanoparticles.
Yeah.
We didn't work with plasmonic nanoparticles, but the fixing is due to albumin coagulation. It's possible, maybe. I think that it is possible.
I would like to continue our discussion a bit later, if you don't.
Thank you. Any more questions? May I ask one? Could you probably estimate the temperature distribution around the focused spot?
We don't measure the temperature distribution. They calculate the temperature distribution, and it is depending on power, about 60 grados.
60 degree, yes. So we cannot work with proteins, with biological objects. Yeah.
Maybe we can work with protein to increasing the laser power. But
Is it
60 degree is the maximum.
is the maximum?
Yes.
But still 40 is the maximum for the proteins.
I know.
Yeah. Another question, is it possible to estimate forces or even to build the field of forces to be able to predict the kinetics in the system?
It is possible to estimate forces, but we do not did this numerically. For point optothermal trap, we measured the separated velocities, and on the base of separated velocities, they estimated the force, but I can't now to
Yeah,
give-
because you know the velocity and the viscosity of the media,
Yes,
so you
yes,
can estimate
yes,
it. Yeah,
yes,
it
yes.
was not done, no?
For point optothermal trap, what we do it.
And how much does it depend on the size of the particle?
Don't understand.
I mean, how much the action, the force, everything is dependent on the size of
In
the particle?
optothermal trap, because all particles transferred by flow, convective flow, there is not
No dependence.
depending on big depending on size of.
So the beam is acting to the liquid actually, not to the
Yes,
particle itself.
yes.
Thank you very much. So, okay, let's applaud again to our lecturer. And The next talk, which will be given by Professor Amendola from Italy, from Padua. Hello, Professor Amendola. And this talk is entitled as Multi-Parametric Investigation of Laser Ablation in Liquid for the Synthesis of Nanoparticles. Please, we give you the floor.
Thank you for your nice introduction and for the opportunity to talk to this important scientific community. So my contribution will deal to an original type of analysis performed on a class of techniques which deals with laser for the generation of nanomaterials. So in the last decades, there is a big scientific community which work on the synthesis of colloids by laser ablation in liquid, where we have a bulk target deep in a liquid environment, and we generate the colloids, so the nanoparticles, by laser pulses focused on the bulk target. Indeed, this technique can be also coupled or modified by irradiation of agglomerates of powders of nanoparticles or of the particles themselves to perform laser melting on fragmentation. These techniques are investigated because they have several advantages. In particular, they allow the production of nanoparticles of different types, so really a library of compounds and structures are available in this way, and they can be obtained by room temperature and pressure operation with limited manual operation in safe conditions, also by a procedure which is generally green and cost effective. And moreover, these techniques are really easy to implement in some condition which is basically automatic, so like a self-standing setup, which can be even controlled remotely with a PC or a smartphone. So ideally, this can be used also for the production of nanoparticles, which can be used as radioisotopes for medical purpose and so on, without the presence of the operator in the production site. So due to these reasons, a lot of studies from the international community, and there are important examples also among the organizers of the ALT conference, work on the development and potentialities and promising features of this pool of techniques which are sometimes defined as laser synthesis and processing of colloids. In particular, the most popular one is the laser ablation in liquid, the first that I mentioned, where we start by ablating a bulk plate in a liquid. In my laboratory, we focused a lot on this technique because it also allows the generation of out of equilibrium alloys, so a lot of nanoalloys, nanoparticles can be obtained in this way, and in particular metastable nanoalloys where more elements which are normally not miscible in ordinary conditions can be mixed to form an nanoalloy by this LAL technique. And the reason is that the laser ablation in liquid has a very rapid formation timeline for the nanoparticles, and this allows to mix and freeze the elements together, also if the thermodynamics would lead to a phase separation. And indeed, we investigated a lot generation of metastable or stable nanoalloys by considering gold iron, silver iron, silver and gold cobalt, or also iron boron, gold boron, and so on. And we studied these nanoparticles from the fundamental point of view to understand which are the conditions which led to mixing instead of phase separation with formation of oxides or core shell structures. Or we use these nanoparticles for generation, this technique for the generation of nanoparticles, which are exploitable for catalysis or for plasmonics, for magnetic plasmonics, with exploiting the gold and silver, which are plasmonic materials, with the iron and cobalt, which are magnetic. And also we studied a lot their exploitation in nanomedicine, especially concerning gold nanoparticles with iron and boron, which are interesting for imaging and therapy of tumors. But in this presentation, I will focus more on the fundamentals of this technique of the laser ablation in liquid, because the chemistry which is involved in the process is quite complex. And we knew this also since several years, because even starting from single element targets, so bulk gold or bulk silver or bulk iron, we see that by changing, for instance, the solvent in which the laser ablation is performed, we get different morphologies or different compounds. And indeed, we have the formation of a plasma phase during the laser ablation. Then we have a cavitation bubble due to the heating of the liquid. And then we have the release of the nanoparticles in the liquid. So we have a lot of interaction, of chemical and physical interactions between the bulk and the liquid. And it is very complex to predict which phase we will get starting from a certain target and a certain liquid. And this is a rather empirical endeavor until now. So the question for us was how can we predict the results of LAL in terms of the chemical composition of the nanoparticles. And we we try to answer this question by a multiparametric and a machine learning approach. I will sketch the general approach now. First of all, we had to select a case study because we cannot take at the moment all the literature about laser ablation in liquid. So we focused on copper-based nanoparticles because copper is an element which has different oxidation states, so the chemistry of the products change with the condition of the synthesis. Copper nanoparticles are of wide applicative interest, and there is also a good number of studies about LAL of copper nanoparticles. So we started with these studies. In particular, we selected 104 articles, and in these articles we found 239 synthesis conditions, which are different combinations of parameters which were used to get copper nanoparticles. From these synthesis conditions, we build a database of 36 features which can be associated to the synthesis experiment. And these features were related to the setup parameters, so the laser, the focal length, the repetition rate, and so on, but mostly to the chemical properties of the liquid, the physical properties of the liquid, and the chemical and physical properties of the solute, which can be some additive in the liquid or also just the gas, like oxygen from air instead of nitrogen or argon and so on. And we focused on a single output to describe the products, which is the mean oxidation state of copper. Of course, the identification of these parameters, these features, and of this output is critical for the results. But this is something that we had to select on the basis of what was actually available from the articles about the LAL of copper nanoparticles, and what can be actually managed by a multiparametric analysis, because too much complex features or output cannot be realistically managed with this number. However, it's clear that this is very critical for the final outcome. So, by focusing to the copper oxidation state obtained by a set of these 36 features, we started first with the simplest approach, which was a linear regression analysis. And then we moved to the machine learning analysis. For the linear regression analysis, we basically seek for a linear correlation between the logarithm of the oxidation state versus the logarithm of each one of the 36 features that we have identified before. However, we found that for the 239 data points, the correlation was very low with the single features. Only get some appreciable results when considering the average of these results. And we found a correlation of an R square, I mean, of 0.64 as the maximum value in case of the number of atoms in solvent molecule. However, this approach was not very satisfactory. It didn't allow the prediction of the outcome of the synthesis, and also the correlation was very low. So we tried another approach by considering the combination of these features to identify which are the relevant features which led to the best correlation. Indeed, also in this case, the result was not particularly exciting. The best combination included 13 over the 36 features from which we started, but the R square was only of 0.31. So it's not really significant. We also applied a more modern approach, which is a genetic algorithm, to reduce the number of features. And in this case, we found that the genetic algorithm identified 11 features which were related to the oxidation state of copper. These features are almost different from the one obtained by the combination of features or superfeatures. But in any case, the R square was still very low, and the genetic algorithm did not allow to predict the oxidation state and to guide to the synthesis conditions which are best suited for a certain product. So to sum up, the linear regression analysis is not a good approach for this problem. It's too complex. So we resort to a machine learning approach by using boosting and bagging models, which are quite common currently, like the XGBoost model, the AdaBoost, the Gradient Boost, or Random Forest, and so on. So we test different models, and in this case we started from the feature reduction, and we obtain a ranking of the features over the different models tested, and we selected the 9 top features in this ranking, which are divided among the the setup parameters, the liquid chemical properties, and the solute chemical properties. We found a good ability of the model to learn from our database with the 36 features, and the R-square were always higher than 0.85 for the training set, and the test set was between 0.55 and 0.75. So the good thing of this approach is that now the prediction of the results of the synthesis is relatively easy with the machine learning models instructed from our training dataset. And with the 9 features, what we did was fixing the setup parameters that we have in our laboratory, like the duration of the synthesis, the repetition rate of the laser, the focal length of the lens, and the pulse duration. And then we considered the parameters of the solvent and the parameters of the solvent. And first, we fixed the parameters of the solute, and we considered different we considered different percentage of the parameters basically were the number of atoms in solvent molecule, or the percentage of some chemical elements which have an oxidizing effect on copper, like oxygen, chlorine, nitrogen, and sulfur in solvent molecule, or the mass fraction of the solute and the percentage of these elements which react with copper in the solute molecule. And so we consider different combinations of these parameters to build a map. In this case, for instance, the map of the percentage of oxidizing elements in the solute versus the percentage in the solvent for a fixed mass fraction of the solute and a fixed number of atoms in the solvent molecule. So by fixing 2 of them and changing the other 2. And we see by these heat maps that the model can tell us which are the range where we get, for instance, a low oxidation state of copper, which is close to metallic copper, or an high oxidation state of copper, which is copper 2, so the completely oxidized copper. And we also see that in general, the region where we can have the copper 1 oxidation state are very tight. And this is the most difficult condition to catch, is the white regions here. With these results, we identified a set of solvents which are solvents and solutes which should correspond with the prediction of the machine learning model. We perform the synthesis and we test the matching of the synthesis results with the prediction of the machine learning model. And we found an R-square of 0.90. So actually we are very satisfied with the ability of this method to predict the chemistry of the copper nanoparticles produced by laser ablation. We also get some insights about the mechanism of the laser ablation in liquid, because now we know that these 9 features connected to the setup, the solvent, and the solute are, according to our model, the most important features for this LAL synthesis. So with this, I conclude. Probably I'm a little bit large in time compared to my slot. I apologize for this. I thank everybody. And I just mentioned this special issue about laser-generated colloids with some discounts available for publication. Thank you.
Thank you very much, Professor Amendola, for your talk, for explanation about oxidation problem and the possibility to predict it. If anybody want to ask the lecturer some questions, yeah, okay.
Hello, can you hear me?
Yeah, I can hear you very well. Do you hear me as well?
Yeah. My name is Professor Khleptsov. My question is it possible to generate or predict from machine learning approach some kind of different shape of particles except for spherical one? What do you know from the literature?
This is a very nice question. Actually, my PhD student, which work on the machine learning models for laser ablation, is also now working about how to, in general,
some problems with connections. Could you repeat, please, your answers?
Happens is that you can switch from aggregated to spherical nanoparticles or elongated nanoparticles to do the formation of chains and so on. But in principle, the answer is surely yes, it will be possible, and we are actually also moving in this direction.
Thank you.
I have a question. Does this approach works only for single component nanoparticles, or can also be applied to the nanoparticles which are composed of several elements, chemical elements? Professor Amendola, are you with us?
Can you hear me now?
Yes, we do.
Okay. I'm sorry, the connection was lost during your question. Can you repeat it?
Yeah, the question was about complex nanoparticles, which are composed of several elements. Is it still possible to predict, to make some prediction about the properties and oxidation state?
I think this is the challenge of the future development of this approach, and it will be interesting to see, to test this method also with the more complex nanoparticles. Also, we are interested in alloys, so we are also looking at this as a possible exploitation. The key point is always the data set. No? The critical point is the data from which we start, how many we have of them, and how good, how reliable they are.
In principle, one could imagine the situation when the target is composed of several elements and they have different oxidation properties. So that would help, for example, to oxidize one of them for the favor of another one, which will be left as much as possible of metallic states and something like this. What do you think of it?
Yes, the point is that from the empirical point of view, this can be cumbersome to find the appropriate condition. And we don't know exactly how to obtain this result very precisely. And we hope that by machine learning we can get case of copper to obtain this result. So in principle, this is one of the targets of the LAL technique. it is possible, but there are a lot of parameters and there are a lot of experiments to perform to find a good condition.
Thank you very much again. Let us thank our lecturer again. So
Thank you.
see you on our next meeting. Thank you for your talk. And at that our morning session is over, so we have a coffee break, and we expect you are coming here in 20 minutes to continue our today program. And so your talk is about precision laser technologies for optical instrumentation.
Yeah.
Please, we give you the floor, 20 minutes.
Yeah, thank you for introduction. Good morning, everyone. My name is Alexander Dostovalov, and first of all, I would like to thank the organized committee for invitation and opportunity to present the results of our work. And previously, this talk should be given by Dr. Viktor Korolikov, but he is not able to do it and asked me to present this. And this talk will be some kind of review of our recent results that we obtained in our institute on precision laser processing of different materials. Here you can see outline of my talk. After short introduction, I will present the results of CV laser based technology for processing of different materials, then processing with femtosecond laser for surface structuring, and finally the modification of transparent materials inside the bulk. So, laser-based system for surface structuring, we can divide it into two main parts. The first one is etching-based technique. Here you can see from the left, and direct laser processing on the right. Of course, laser radiation is used in both in these techniques, but main mechanism of material removal is different. In the first case, it's etching process, and the second mechanism, it's direct ablation by laser radiation. And in case of first etching-based technique, we can also divide on two parts. In our case, the first one is optical lithography, and the second one in thermochemical assisted processing. Processing of thin chromium film in our case, and this technique for micro machining of different thin films was proposed in a group of Professor Vadim Veiko in ITMO. And after that, in our institute, we also studied this effect extensively and developed new methods for creation different diffractive elements. And after that, I will present the results of femtosecond laser-based technique. Here you can see on the right side that we can divide direct laser processing depending on the pulse duration onto two parts, big parts. The first one is short pulses or CV laser radiation, and the next one is femtosecond-based technique. So let's start with CV laser processing. Here you can see an etching process. And here, from the left side, you can see the typical process of photolithography. It means that we can pattern photoresist layer by laser radiation, and then we can etch this by solution, a developer solution, and using dry etching technique, we can transfer this profile that we obtain on the photoresist into the transparent substrate. And the next one is thermochemical assisted technique that is based on oxidation of thin chromium films under action of laser radiation that we can see from the right side. And after that, after selective wet etching, we can remove thin metal chromium film, and also using dry etching, we can transfer this pattern to the substrate. Using this technique, we can write in two different ways. The first one is XY coordinate system, and the next one is polar coordinate system. Both of them have different advantages and disadvantages. For example, in the first case, we can obtain high linear precision of patterning and high constant speed. But here you can see some disadvantages of using this technique. The first one is low processing speed, because you need to start and stop, and also to write different circular shape or trajectory by this technique. And for this reason, polar coordinate system can solve this problem, because you need, in this case, you rotate your substrate and write on the polar coordinate, and in this case the circular trajectory is the best pattern to do it. And also we can use very high rotation speed and process substrate with relatively high speed. And for this reason, in our institute, this technique was used for production different diffractive optical elements. On the setup presented here, you can see laser radiation was focused by high numerical aperture lens on the substrate, and this substrate was rotated with high rotation speed, up to 12 revolution per second. And radiation translation was done by high precision linear stage with interferometric feedback mechanism. And using this technique, we can obtain different diffractive optical elements, that is especially important for testing metrology testing of different optical elements, especially for high space telescopes, because in space telescopes there are many different spheric surfaces, and we should check it to do the right optical scheme. And maybe you know that some funny story, not funny, story about Hubble telescope, because in Hubble telescope one lens mirror, main mirror, was done with some mistakes on the Earth, and after that, after launching this telescope on the space, the obtained images was not so good as was expected from calculation. And the reason of this that during production of this main mirror, one engineer mistaked in production of that element, and the cost of this mistake was around $50 million to correct these mistakes in that. And how we can check the rightness of production of our mirrors? We can calculate wavefront. We can calculate our computer-generated hologram to provide correct wavefront, and we can after that we can compare the wavefront from our diffractive elements with wavefronts that we obtained from our mirrors. And using this technique in 2011, in our institute, we produced different diffractive optical elements to test main mirror segments of James Webb telescope. And as you can see, now we can obtain very nice, very beautiful picture of our universe as a result of this work. And it means that the precision and quality of our diffractive optical elements is very high. And of course, several years ago, in our institute, new equipment was purchased and set on operation. It's XY photolithography system, and in comparison with previous setup, we use XY stage for moving the substrate, and also the beam was scanned by acousto-optic modulator in this case. And here you can see the example of patterning of silicon substrate with very narrow lane width. And here you can see the example, another example of this production. It's an array of lens that we obtained on silicon substrate and quartz substrate for Schack-Gartman wavefront sensors with different diameter of lenses and aperture up to 0.2 and high efficiency. But this story was about CV laser, but development high energy and with low pulse duration, I mean ultra-short laser, provide us opportunity to increase our precision of microfabrication. For example, you can see the comparison of metal foil drilling by nanosecond pulses on the left with the same pulse fluence with femtosecond pulses on the right. And here you can see that in the first case we see a large heat affected zone, we see the unstable age of the holes. But in the second case, we obtain very nice, very beautiful holes. What is the reason of this? The reason of this is the time interval of our laser pulses. In the first case, the time interval is nanosecond is very large in comparison with electron phonon relaxation time, and in this case, the main process of ablation of the materials is main process of this is melting of the materials in this case, and for this reason we see that this process is unstable, and for this reason we see that shape of this crater is not so nice, is not so narrow. But in case of femtosecond radiation, the time scale of pulse duration is very short. It's shorter than this time of electron phonon relaxation time. Is around 10 or 1 picoseconds. And in this case, the high temperature, high pressure value can be obtained in the small focal area of laser radiation. It means that we can vaporize the materials without melting, and in this case we can obtain very fine, very precision modification in this case. But this advantages works not only for metals, non-transparent materials, but also for transparent materials. Here you can see the comparison of microstructuring of glass by nanosecond pulses on the left. Here you can see the cracks, the different defects on the edge. But in the case of femtosecond processing that was obtained in our institute on the glass, here you can see on the right, we can obtain very nice, very narrow channels on the glass. And for this reason, femtosecond laser radiation is a very remarkable technique, a very useful tool for microprocessing of different materials. And in the laboratory of Dr. Viktor Besmeltsev, 3D structuring and special setup was developed. And in this case, we can process different materials by using scanners on the small area, let's say 5 millimeters on 5 millimeters, with galvo scanners with high speed of up to 1 meters per second. But using high precision linear stage, we can shift this area on one place to another and provide very high, very large scale devices. And here you can see the examples of surface macrostructuring of the glass on the left, also hole drilling on the silicon substrate, and foil cutting and foil processing on the left on the bottom, with width of this small feature of around only 15 microns. Also, we optimized and we find optimal parameters for processing glass using multiple layer by layer inscription, layer by layer ablation. And in this case, we can obtain very high quality channels with very high, with very low roughness, less than 1 micron in this case. For example, with perspective application in micro chips, let's say. Here you can see biochips. And also microstructuring of materials is a very important tool for processing anti-reflective microstructuring. in high refractive index materials. For example, for gallium selenide, we have a refractive index of around 0.5. It means that we obtain very high Fresnel losses. In comparison with glass, we obtain only 4% of Fresnel losses, but with increased refractive index, these losses also increases and achieve about 20% in case of gallium selenide. And using traditional techniques for anti-reflection coatings, it's not in the case in our for this material because adhesion problem. The typical anti-reflective coatings is not works well in this case. And alternative solution is produce some microstructuring by ablation to decrease the refractive index on the air material interface. And here you can see how it works. And using this technique, we can increase the transmission of our sample of gallium selenide from 65% to 94%, writing arm from one and from another side. And now I would like to present our results on bulk structuring of transparent materials with femtosecond laser radiation. In this case, femtosecond radiation can produce very high intensity in focal area, such intensities of around 10 terawatts per centimeter squared. At such intensities, multiphoton ionization starts, and it means that we can obtain very hot electron-ion plasma in the focal area that leads to fast heating, melting, and resolidification of materials inside the focal area. And depending on the fluence of our radiation, we can obtain different types of modifications. The first one is refractive index change. The next one is birefringent formation and void formation at higher energy. And also, in case of femtosecond radiation, we can see the time scale of different physical processes, and we can see that absorption of the radiation absorption of radiation is shorter than electron phonon relaxation time. Here you can see that it's around 1 picosecond. It means that we can absorb laser radiation without thermal diffusion from the focal area. It means that we can obtain area of experimental parameters, that we can obtain refractive index change without material damage, and to inscribe, for example, such different structures. For example, fiber break gratings. Fiber break gratings is periodic modulation of refractive index inside core, fiber core, that reflects light from wide spectral to narrow one. And the resonance wavelength of this reflection will be depends on the period of FBG and also the refractive index of the core. And in this case, we can use this fiber grating as mirrors in fiber lasers, also as sensors in fiber sensors, because as we can see that temperature change or deformation will lead to change in periodicity and leads to change in position of reflection wavelengths. And traditionally, the FBG was inscribed by ultraviolet radiation and phase mask technique that was presented on the left side. And in this case, phase mask provides interferometric pattern in the fiber core, and the period of FBG depends on the period of this phase mask. That is not convenient for inscription different FBG with different wavelengths, for example, for sensor applications. And in our case, in our work, we use point-by-point writing technique that was presented on the right side here, where each grating pitch was produced by single laser pulses during the translation of the fiber with constant speed. In this case, the period of FBG depends on the velocity and the repetition rate of the laser. And in case of using femtosecond radiation, we can obtain another different advantages, such as different profile, period, and also possibility to writing through the transparent coating, okay? And to produce some structure, we can see experimental setup. Here you can see the structure of EBG. And it's very can be produced in multi-core fibers. You can see the array of multi-core fibers, and I was presented on the Monday, and I will skip it in a fast way. Here you can see the results of reconstruction of different shapes of this using these sensors. And the last slide of our presentation, the previous results was obtained by Gaussian beam. It means that you, for patterning some samples, you need to focus your radiation on some spot and produce patterning, but laser-induced periodic surface structure provides a new opportunity to microstructuring of materials. It means that we can produce sub-micron structures with using spot size of around 100 microns. It means that you can produce very, very high numbers of periods with high regularity. Here you can see the regularity obtained on the titanium, chromium with 2D structure to tailor optical and chemical properties of the material. Here you can see the diffraction of these gratings. So, in conclusion, the first satellite technology for microstructuring of different materials based on CV laser was developed and used for different diffractive optical element production. Flexible technology for microfabrication based on femtosecond as on surface as well as inside the transparent materials was demonstrated for different applications. Thank you for your attention.
Thank you. Thank you in turn for the very interesting talk, which is very much grounded to some application issues. Questions, please?
My question concerns the spectral characteristics of fiber Bragg gratings. Could you please show the slide? Okay.
That one?
The next one. What is the reason for the side lobes we see here in reflection, and what is the transmission spectrum?
The transmission spectra, you mean the absorption losses? No?
I mean how looks the transmission spectrum?
Yeah, it's transverse view.
Reflectivity.
Yeah. If in case of low absorption losses, it is the case, yes. But in case of high reflection spectra, we also obtain some resonances with cladding modes. It means in transmission we can some peaks on the left side on our transmission spectra. Mm-hmm. Yeah, it's typical transmission spectra for point-by-point writing.
And what is the reason for the side lobes in the reflectivity?
The side lobes reflectivity, it means that we don't use pedization. We use only constant energy in our case, and if we plot the distribution of delta n along the fiber, we obtain some how to say not rectangle shape, square shape, yes. And for this reason, this shape leads to such side lobes. But if we use some apodization looks Gaussian, we cannot. In this case, side lobes should disappear, and we should try it in the future. Yeah. I would like to say that this comparison between calculation and experiment, and here you can see that comparison is quite nice. It means that these side lobes from the theory.
Thank you. As a chance for one more brief question, please.
Thank you for your presentation. We in Samara used two types of laser writing station. One manufacturer headed by Alexander Polishuk, 24, and other manufacturer headed by Yuri Chuguy, 2014. Александр Григорьевич Юрий Васильевич нет с нами, но дело их живет. My questions. Are you ready to manufacture a new version of laser writing station, and what parameters and features we can waiting for a new version of such a laser writing station?
Thank you for your questions. Very interesting. I think that I should address this question to Karlikov, because Karlikov Victor is now responsible for that task, and I will ask him about this plan, and I can answer you by email.
Let us thank Professor Dostovalov again. And go on to the next point of our program, which will be presented by Professor Sokolov from Federal Research Center of Crystallography and Photonics, Russian Academy of Science, Moscow. And the talk is entitled High-Speed Integrated Optics on the Base of Fluorinated and Composite Polymer Materials. Please.
Good morning, colleagues. Mr. Chairman, in my talk today, I would like to speak about high-speed integrated optics on the basis of new fluorinated, highly fluorinated, and composite polymer materials. And these investigations were carried out in the Institute on Photonic Technologies, Federal Research Center, Crystallography and Photonics. I would like to start with description of new optical materials on the basis of highly fluorinated and fully fluorinated polymers and the benefits of these new materials for integrated optics and photonics. These benefits are extremely high optical transparency, very low refractive index and material dispersion, very high destruction temperature, and so on. Later, we will discuss different laser technologies for fabricating polymeric optical devices like single-mode and multi-mode waveguides on different surfaces using these highly fluorinated materials. And the technologies I will discuss, they are UV contact photolithography, direct laser writing, laser photo bleaching, and so on. Also, I will discuss the implementation of these new polymer materials in integrated optics. I mean the fabrication of different devices like high-speed optical bus on printed circuit board for microprocessor computing systems, and narrowband waveguide grating filters, which can be laser-induced in polymer waveguides, and optical multiplexers, demultiplexers based on these waveguide filters. well, and in the second part of my report, I will talk about polymer nanocomposite materials. These materials are fluorinated crystals embedded in the polymer matrix. The crystals are doped with rare earth elements and can be used for fabricating compact optical waveguide amplifiers for 1.5 telecom wavelength region, as well as high-speed electro-optical modulators on the base of polymer matrix with embedded electro-optic chromophores. And in conclusion, I will try to discuss the brilliant future of fluorinated polymer materials in photonics. Mr. Chairman, should I consider my talk in English or in Russian? For me, it's equal.
It's a tradition of our meetings, so all the talks and the discussion are given in English, please.
Okay.
Yeah.
So, let us consider the benefits of highly fluorinated amorphous polymers. These benefits are, as I mentioned, extremely low absorption in all three telecom wavelength regions around 0.85, 1.3, and 1.55 micrometers, low refractive index, and low material dispersion. Also, these polymers have very high destruction temperature, higher than 400 degrees, and this is because the energy of hydrogen fluoride links much higher than the energy of destruction of carbon hydrogen band. It is well known that in the telecom wavelength region, the frequency of absorption bands is stipulated by stiffness constant K and reduced mass. So, if in the polymer macromolecule we replace the light hydrogen atoms by heavier fluorine atoms, we reduce the effective mass, and in this way we shift the absorption band to longer wavelengths. As a result, the transmission windows are opened in all three telecom wavelength regions. It is interesting to note that according to theoretical precisions, completely fluorinated polymers have extremely low absorption losses in the 1.5 wavelength region, around 0.15 dB per kilometer. It is very close to the absorption losses in modern silicon fibers. Up to now, this high transparency was not received in the worldwide laboratories, but we hope that it will happen in the future. Also, the perfluorinated polymers have very low refractive index and very low material dispersion, the right figure. This material dispersion is even lower than the material dispersion of silicon fibers. And among the organic materials, the fluorinated polymers have the absolute minimal value of refractive index around 1.29, the left figure. Why is the material dispersion so important? It is important because it increases the transmission band, and using such materials with low material dispersion, one can increase the data transfer rates in polymer waveguides. It is important to note that the perfluorinated materials can be of two kinds, polycrystalline and amorphous. What we use with amorphous materials because they have very low Rayleigh scattering. And the films made of these materials are highly transparent. In this figure, you can see the examples of fully fluorinated polymers which were produced in our laboratory. I would like to note that to fabricate such polymers, we use the high pressure technique. It means we employ the pressure from 15 to 16 thousandths of atmospheres and the temperature 120 up to 200 degrees centigrade. Why? The reason is that many perfluorinated monomers cannot be polymerized using radical polymerization reaction under normal condition because of steric effects, steric hindrances. This is why we use the high pressure. Just to feel what this high pressure means, it is known that in the Pacific Ocean there is a Mariana Trench, the deepest place in the ocean. The depth of the Mariana Trench is approximately 11 kilometers, and the pressure at the bottom of the trench is around 1,100 atmospheres. But what is more important, the density of water at the bottom of Mariana Trench is increased by approximately 5%. In the high pressure reaction cell, in which the polymers are synthesized, the pressure is 15 times higher. So the density of liquid monomers is increased by 10 to 15%. It results to the change in the electronic structure of the monomer molecules, and in this way, these monomers can take part in the radical polymerization reaction, which is not impossible under normal conditions. Another class of highly fluorinated polymers are acrylates. These polymers are partially fluorinated, and in this case, they do have high reactivity. So to fabricate waveguides using these liquid monomers, we use UV lithography. In this figure, you can see the idea of the contact lithography method. The liquid composition is located between the polymer buffer layer and the silicon photomask and is illuminated by UV radiation. The illuminated regions polymerize, whereas the regions which are not illuminated are liquid. So using conventional wet etching, one can fabricate the multi-mode and single-mode polymer waveguides on different surfaces. Here are 3 steps of this process. The first one is fabrication of the substrate. For example, on the standard printed circuit board, the polymer buffer layer with low refractive index, then fabricating polymer waveguiding cores, and finally covering this waveguiding cores with a polymer with low refractive index. And on the right-hand side, you can see the photographs of the array of polymer waveguides on the printed circuit box, up figure, and same photograph of single-mode polymer waveguides fabricated on silicon substrate. Well, one of the important implementation of polymeric materials is fabrication of high-speed optical bus on the printed circuit board for microprocessor computing systems. It is well known that data transfer inside the silicon processor is very high, up to 6-7 gigabits. But what is the bottleneck of this technology is the reduced data transfer between the individual CPU units on the printed circuit board. To increase this velocity, this data transfer, there was suggested to use arrays of polymer waveguides. So the interconnections, electrical interconnections on the basis of copper metal wires are replaced by the array of polymer waveguides. And almost all world-known companies which deal with microprocessors like IBM, Intel, and so on, they are involved in this activity. In the right corner of this slide, you can see the optical bus, green optical link, which was developed by the IBM company. One can see that the level of integration of waveguides in this optical link is approximately 142 waveguides per centimeter. We have shown that by using deep UV contact lithography, it is possible to essentially increase the level of integration. What we have done, the level of integration about 625 waveguides per centimeter. Here you can see the first optoelectronic printed circuit board, which was fabricated in Russia in our institute in cooperation with NISI of the Russian Academy of Sciences. On the left-hand side, you can see the printed circuit board optoelectronic in the laboratory, and on the right-hand side picture in the computer frame. This optoelectronic board has 12 channels. The optical data transmission velocity is around 10 gigabit per second per channel, and it was restricted only by the possibilities of our measurement equipment. Attenuation loss is less than 0.05 dB per centimeter. It works at the datacom wavelengths, 150 nanometers. So by using this technique, it is possible to use highly fluorinated polymer materials to provide multi-level optical bus. In this construction, the polymer waveguides are located in different regions of the multi-layer printed circuit board. It is possible also to fabricate the polymer waveguides on the flexible plastic substrate, and in this ways to provide the connection of the optical interconnects on the cross panel with optical interconnections on the daughter boards. Another task which was solved in our laboratory is the fabrication of narrow-band Bragg grating filters in polymer waveguides. We used the laser technique, illumination of the polymer waveguide through the phase mask, using the helium-cadmium laser, 3 to 5 nanometer wavelengths. Here you can see the photograph of the polymer face mask, which was fabricated by making replica from master grating in indium phosphide. And by varying the refractive index of these polymer relief gratings, it is possible to adjust the intensities of the 0 and -0 diffraction orders. And here you can see the transmission characteristics of this grating filter. The width of the reflection band is 0.4 nanometers, which corresponds to the international standard. And these Bragg gratings are apodized, so no side lobe absorption peaks. So let me shortly discuss the fabrication of fluoride crystals, nanocrystals, doped with rare earth elements, core shell nanocrystals. Here you can see the photographs of such crystals. One can see the hexagonal structure, which corresponds to the beta crystal phase. It is interesting to note that by using deep UV optical microscopy, the wavelengths 248 nanometers, one can take optical photographs of such nanocrystals, the right figure. When these nanocrystals are embedded in the polymer matrix, they have very high down conversion photoluminescence in the C-band telecom wavelengths region around 1.5 micrometers. Okay. In this slide, you can see the compact polymer waveguide amplifier, which was fabricated in our lab. On the left-hand side, you can see the polymer waveguide with embedded nanocrystals doped with rare earth elements. On the right-hand side, you can see the scheme of the amplifier. The waveguide is illuminated by 977 nanometers laser pulse, which excites the erbium atoms, and the signal pulse and at 1.5 micrometers takes this energy from the excited erbium atoms, in this way is amplified. In the right-hand side picture, you can see the dependence of optical gain versus the pump power. The next technology we have developed deals with fabrication of composite fluorinated materials with embedded electro-optic chromophores. Okay. Also, fluorinated polymers are very important for this technique. And in conclusion, I would to say a few words about benefits and promising future of fluorinated polymers. So, fluorinated polymers can be used for high-speed telecommunication, making polymer optical fibers, high-speed optical bus on printed circuit boards for microprocessor computing systems, compact waveguide amplifiers, as well as DBR, DFB waveguide lasers, optical modulators, high-speed modulators, and optical multiplexers, demultiplexers on the basis of break-grating waveguide filters. Thank you for your attention and patience.
Thank you for your presentations very much, which was very interesting and promising, really a breakthrough in technology in nearest future. I was very much sorry to interrupt you because we are running out of time. So only one short question, please. Okay, I will ask. Fluorinated polymers are known for the high scattering of light. For example, a Teflon, everybody knows it is white. How do you solve this problem in your case?
Correct. There are two types of fully fluorinated polymers. The first type is polycrystalline, like Teflon. They suffer from very high scattering. And another type we use are amorphous polymers. They are fully transparent, and the films of these polymers look like glass or PMMA. But in contrast to PMMA polymer, for example, which is transparent only in the visible region, but not transparent in the near infrared wavelength region, the fully fluorinated polymers have very low absorption in this near infrared region too. And this is the difference between conventional hydrocarbon and fluorinated polymers.
Thank you. I'm so curious and cannot not ask another one question. You mentioned that you adopt with erbium using some nanostructures. Why not to adopt it directly?
A very good question. Of course, one can introduce the erbium atom in the polymer matrix, but the quantum yield in down conversion is very low because of the surroundings, organic surrounding of this atom. However, the erbium atom illuminates very well when it is inside the crystal. So what we do, we make the very small crystals with a dimension smaller than the diameter of the polymer waveguide and introduce these crystals into the polymer matrix.
Matched by refraction index to the matrix?
It depends. To some extent, it is possible to change the refractive index of the polymer matrix, and if it is equal to the refractive index of the crystal, we will have no scattering at all.
Thank you. Thank you very much again. We invite the author of the next talk. The next talk is given by Professor Oxengenda from Tashkent. Is he present? Is he present here? Seems to be not. So let us skip it and go to Golyshev, to Professor Golyshev. And the question to our technical team, is the presentation of Professor Oxengenda is given remotely or not? Is he online or not? He is not online. He is not seen at the system. Okay. So we are coming to the talk which is entitled Amplification of Scaling Law to Describe Laser Cladding of Metal Ceramic Coatings. Please, Professor Golos.
Thank you. Коллеги, прошу прощения изначально, что презентация на русском. Видимо, в какой-то момент я упустил, что конференция имеет чисто английский язык. Вот, еще раз приношу извинения, но, к сожалению, без ноутбука не получилось исправить презентацию и подготовить доклад. Но я надеюсь, что так тут у нас все русскоязычные, это небольшая проблема. Данный доклад немножечко еще выбивается из тематики данной конференции, потому что он посвящен применению подходов механики для описания процессов, протекающих при лазерно-аддитивной выращивании. Если говорить про аддитивное выращивание, то, или 3D-печать, да, то на сегодняшний день их огромное количество. Но если сделать упор именно... Так, понятно, указка не указывает. Но если посмотреть именно про лазер, то это получается 4-я, 5-я, да, колонка, где вот красные точки, как будто бы лазер светит, да. То есть это две технологии, когда у нас подается вместе с лазерным лучом порошок через сопло, либо он уже помещен на подложку, и лазер сканирует материал, который наплавляется. Вот. И в основном мы будем говорить про вот эти две технологии. Если копнуть чуть глубже, то вообще говоря, процесс лазерной наплавки, либо аддитивное выращивание, это вообще многопараметрическая задача, которая включает в себя очень много всяких процессов, начиная с исходных данных, да, какой тип лазера выберем, какую длину волны, потому что можно и 10,6 микрон взять СО2 лазер, можно 1 микрон взять, 1,07, да, тербиоволоконный лазер. И у нас уже коэффициент поглощения будет меняться, следовательно, будет влиять и на физические процессы, формирование ванны расплава, да, как там будет изменяться плотность мощности. И все это будет сказываться на конечном результате, именно на физико-механические характеристики и структуру формируемого материала. Ну, если более подробно, то при взаимодействии лазерного излучения с веществом, то у нас там происходит поглощение. Если очень высокая плотность мощности, будет формироваться так называемый парогазовый канал, то есть сразу будет происходить испарение материала, и все вот эти многочисленные процессы надо учитывать. Соответственно, на сегодняшний день существует очень много различных теоретических исследований, да, как лазерное излучение воздействует на порошковый материал, формируется ванна расплава, формируется так называемый единичный трек. Но все вот такие вот исследования, да, вот тут вот другая работа представлена профессора Ковалева, который тоже рассчитывает, пытается оценить, как будет формироваться вот этот единичный плавочный валик и сравнивать даже с экспериментами. Но все такие численные модели, они немного ограничены, потому что все равно не ясно коэффициент поглощения, да, потому что там будет происходить многократное отражение, соответственно, просто по Френелю там не оценить. И если подытожить, то, вообще говоря, сложность численного моделирования — это большие вычислительные ресурсы надо, потому что задача многопараметрическая, там начиная с термодинамики, гидродинамики и так далее, надо все эти процессы учитывать. Большие временные затраты и нехватка исходных данных. Поэтому введение безразмерных чисел на основе пи-теоремы позволяет немного упростить физическую модель процесса, выявить соотношения, лучше определяющие соотношения между физическими величинами и найти вот определяющий закон, описывающий протекающий процесс. Как я и говорил, в нашей работе мы будем исследовать два процесса аддитивного выращивания, два основных процесса. Первый — это Direct Metal Deposition, это когда у нас порошок подается через коаксиальное сопло, соответственно, с лазерным излучением, и происходит наплавка материала. Второй процесс — это Laser Surface Cladding, или по-другому это SLM технология, Selective Laser Melting.
Это когда у нас насыпается на подложку слой порошка, лазер сканирует порошочек, столик опускается на заданную толщину, и происходит такое постепенное выращивание какой-то детали. Вот. И мы попробуем сравнить эти технологии, посмотреть, вообще говоря, сильно ли они отличаются по физике. Вот здесь вот представлены картинки так называемых единичных треков наплавленных. То есть у трека есть, грубо говоря, высота трека, ширина трека и насколько глубоко мы проплавляем материал в подложку. Вот. Ну и, соответственно, зная эти три параметра, мы дальше можем уже выращивать в сторону, вверх. Но как понять, какие геометрические параметры у нас получится в результате лазерной наплавки? Вообще говоря, вот эти все процессы, это является функцией от многих переменных. Мощность излучения, скорость излучения, скорость сканирования лазерным излучением, диаметр пучка, теплофизические свойства материала наплавляемого. И, конечно, можно использовать пи-теорему, пытаться там какие-то соотношения находить. Но мы немножко пошли по другому пути и использовали методы подобия размерности, взяли числа безразмерные, которые учитывают, ну, точнее, так сказать, числа, которые используются в различных направлениях физики, то есть там число Пикле это все-таки больше газодинамика, безразмерная энтальпия это теплофизика, число Френеля это, или число Марангони это уже больше гидродинамика, и попытались посмотреть, а будут ли они работать в нашем случае. Ну, так как это начальная работа, мы вначале посмотрели два параметра, это энергетический параметр, то есть безразмерная энтальпия. Он заключается, что пусть там у нас некая энергия поглотится, некое время, далее эта энергия распространяется в неком объеме материала, и если мы это все обезразмерим на энтальпию плавления, то у нас формируется такая вот безразмерная энтальпия. Причем мы можем выделить две составляющие. Первое – это теплофизические процессы, точнее теплофизические константы. А второе, это вот красненьким выделено, это вот параметры, технологические параметры, которые задаются на установке. То есть мощность излучения, скорость сканирования и диаметр пучка. А второе, это динамические параметры, это число Пикле. Фактически это отношение скорости распространения луча к скорости распространения тепловой волны внутри материала. И в данном слайде показано вот как раз обезразмеренные геометрические параметры, обезразмерили на диаметр пятна, который у нас находится на поверхности материала. Вот, и взяли и обезразмерили все эти геометрические параметры на диаметр пятна и посмотрели, как от энтальпии. Видно, что для двух технологий, а в данном случае происходит наплавка просто нержавеющей стали, то эти все технологии описываются линейной зависимостью. Причем высота трека вообще имеет одну и ту же зависимость, грубо говоря, точки легли на одну кривую. В других случаях они немножко разошлись, но все равно линейная зависимость. Вот число Пикле тоже видно, что все экспериментальные точки характеризуются единой такой гиперболической зависимостью, причем вне зависимости от технологии наплавки, технологии нанесения материала. А что если мы будем использовать уже не... нет, вот еще тут слайд, да, есть. Зачем это надо, вообще говоря? Ну, взяли, описали каким-то безразмерным параметром. А если мы еще введем такой параметр, как коэффициент формы единичного трека, то есть, грубо говоря, который определяет, сильно глубоко мы проплавим, либо не сильно глубоко проплавим в подложку, и нанесем его, то мы можем уже сделать некие технологические умозаключения, которые помогут операторам. Потому что когда у нас число Пикле маленькое, то у нас формируется так называемый режим кинжального проплавления. Там всегда будут поры, что это сразу не надо. А так как мы знаем, что вот эти безразмерные параметры энтальпии и Пикле — это фактически функции от трех основных параметров, то мы сразу можем технологические карты составить и сказать, в каких режимах надо наплавлять, то есть сразу у нас как прикладная задача решается. Дальше, ну, говорили про нержавейку. Что если мы будем наплавлять металлокерамику? Потому что, добавляя керамические частички, мы сразу улучшаем физико-механические свойства материала. Здесь немножко сложнее задача, потому что тут уже мы не просто берем теплофизические свойства материала, а здесь надо уже какое-то правило смеси, да, применять. Если для плотности и теплоемкости мы можем просто по правилу смеси это все дело рассчитать, то для теплопроводности тут немножко сложнее. Мы взяли формулу у Миснера, которая вот, ну опять, да, которая определяется так, и посчитали. И что же у нас получается? Что опять же видим, что все экспериментальные точки у нас ложатся на одну кривую. Вот тут вот представлено 0%, то есть чисто ВТ6, 10% керамики по массе и 20% керамики по массе. От числа Пекля аналогичные зависимости получается. То есть мы опять можем здесь показать, вывести некие технологические карты и показать, что вообще говоря, все это многообразие описывается двумя параметрами. Но когда говорим про металлокерамику, то тут надо понимать, что первый-то слой мы наплавляем на подложку, а второй-то идет уже на металлокерамику. Будет ли там выполняться все это дело? И действительно вот показано, что последующие треки также выполняются эти законы, то есть все это очень хорошо описывается одними и теми же зависимостями, как от безразменной энтальпии, так и от числа Пекле. Для чего же это надо все? А это надо для того, чтобы создавать уже такие сложные функционально-градиентные материалы. То есть в качестве примера я тут вот показываю уже некие такие массивы, которые можно варьировать как различные материалы. Да, здесь вот показано различные металлокерамики можно варьировать. Ну, чтобы вот до этого дойти, надо вот пройти вот этот фундаментальный уровень понимания, как формируется единичный трек. Вот, можем также изменять концентрацию постепенно. И такие вот материалы, они сейчас широко используются и пытаются применяться на различных отраслях, назовем так. Выводы. Ну, основной вывод показано, что, вообще говоря, вот, были найдены определяющие безразмерные параметры, которые описывают именно вот процесс формирования единичного трека при лазерной наплавке. И показано, что, вообще говоря, они определяющие и не зависят ни от типа технологии лазерного выращивания, так и не от типа материала. То есть это вот некое такое вот обобщение. Спасибо за внимание, готов ответить на вопросы.
Thank you for your presentation. Let's switch again to the English, please. Any questions, please?
Во-первых, вот это вот кинжальная, она кинжального-то никогда не бывает, они всегда такие округлые. Ей же все равно, что туда тепло, что сюда тепло, поэтому они всегда вот...
Нет, если высокая плотность мощности формируется, то у нас сразу формируется парогазовый канал, то есть материал сразу испаряется, и лазерное излучение туда уже вот так вот проходит. То есть уже не за счет теплопроводности,
А за счет чего?
там пустота, материал испаряется сразу же, там высокая плотность мощности, там плотность, если достигается там 10,9 Вт на кубический миллиметр, то есть большие плотности мощности, у нас материал сразу будет испаряться.
Ну это что, потоком пара эти частицы вверх, что ли, поднимаются? Как это вообще понимать? Ну ладно, это может потом. И еще я хотел спросить, вот эта безразмерная энтальпия у вас там 10, 12, 15, она всегда порядка единицы, ну 2 энергии плавления и все. А как там можно 10? 10 это какой-то перегрев сильный, по-моему. Так разве работает? Там всегда энергию вкладывать, ну, расплавить, ну, может, с запасом. То есть он, казалось бы, всегда порядка единицы.
Ну вот экспериментально показано, что нет.
А у вас там от 1 до 15?
Да.
То есть бывает даже 15, да?
Да.
То есть
Ну экспериментально вот рассчитан.
сильно перегретые, да?
Ну там смотреть надо теплоотвод, конечно. Ну, вообще говоря, да, то есть у нас же еще зависит вот масса прилетающая вот порошка, да. Если она большая масса прилетающего порошка, там энергии надо больше, поэтому как бы.
Понятно. Спасибо большое, очень интересный доклад. И вот вы правильно сказали, там есть действительно вот эти вот эта его фамилия. Ну там на самом деле, там эти порошинки всегда, ну, в 2-3 раза меньше этого трека. Так не бывает. На самом деле в трек у вас миллиметры, а по расширенке 20 микрон. Поэтому они никогда этого не могут взять, конечно, в расчет не возьмешь. Поэтому вот то, что вы вот это затеяли, очень это похвальное такое начинание, я бы сказал. Спасибо.
Thank you. More questions, please. If possible, could you comment about correlation between these enthalpy calculations and the mechanical properties of what is finally obtained?
Можно на русском, да, ответить?
Если вам так уж совсем...
Да, как-то я вот не подготовился. Еще не проводили, не коррелировали механические свойства с этими параметрами. То есть это будущее.
Because you mentioned some porosity and so on, and overheating is high, so you can expect some generation of vapor, things like this.
Vapor or track?
Yes.
We don't see vapor or...
You do not see porosity.
Yeah.
Okay. Okay, thank you. No more questions. Thank you again.
Нет, это керамические частицы, это просто картирование.
These are particles.
Картирование, вот верхняя картинка и нижняя, это одно и то же. Просто это картирование сделано и закрашено. Закрашено. Microsoft специально делает так, чтобы контрастно было видно. Зеленый это титан? Нет, зеленая это керамика B4C, а черная это вот титан.
Thank you. We invite the next speaker of our session, Professor Khabulin. Is he online? Yes. Please start the presentation.
Do you hear me?
Yes, we hear.
And
But
I don't see the button to share my screen.
Yeah. We are waiting for. For it.
Yeah.
Not yet. Just a moment. Yeah, it's coming.
Yeah. Can you see it?
Yes, we see your screen, but we do not see the presentation yet.
Let's do it. Try again. Stop sharing. How can I do it?
Meanwhile, I will announce the talk. It is entitled Terahertz Quantum Cascade Lasers with Resonant to-Photon Design. And the talk is given by Professor Khabulin from Makarov Institute of Ultra-High Frequency Semiconductor Electronics, Russian Academy of Science. Moscow.
Thank you very much for introduction. But I cannot share my PDF file. Maybe some organizer can help me, because
Hello.
my screen maybe this. And right now, you cannot see it.
Yeah.
You can?
Yes.
It's okay?
Yeah. It's an editing. Yeah. Now it's perfect. You can start, please.
It's perfect. Okay. Thank you. Thank you very much. So, hello to everyone. First of all, I would like to thank all the organizers for the opportunity to participate in such a great conference. Unfortunately, this year I can't attend the conference in person, so I'll do all my best to catch your attention and tell you the most interesting results in the field of quantum cascade lasers. And today I'm going to talk about the development of novel design for terahertz quantum cascade lasers, which we call resonant to-photon design, and its experimental realization utilizing two different growth methods, two different epitaxial methods. This work was done in the Institute of Ultra-High Frequency Semiconductor Electronics and Moscow Institute of Physics and Technology, which I represent here, and in a collaboration with my colleagues from Belarusian State University, Dmitry Ushakov and Alexander Afonenko, and Institute for Physics of Microstructures.
I'm sorry.
Sergei Morozov.
I'm sorry
Yeah.
to interrupt you. We've lost vision of your presentation. Just a moment. Yeah, it's coming again.
Coming again, maybe.
Yes.
Now?
Yes, we see it.
Okay. Okay, so here you can see the original idea of two-photon laser scheme, which was proposed in 60s by a Nobel Prize winner and one of the fathers of quantum electronics, Alexander Prokhorov. In such original scheme, a single electron relaxation between quantum levels leads to simultaneous emission of two photons. It was predicted theoretically that you can achieve more output power and get emission of any frequencies within these two-photon relation. However, the experimental realization of two-photon laser was rather challenging due to the difficulties to find an appropriate platform, an appropriate material platform for this idea. It is well-known fact that terahertz quantum cascade lasers can operate with dual lasing channel, and here you may see the examples of terahertz QCLs with two optical transitions in active model realized by band engineering. However, the activation of these transitions is achieved at different bias points, which correspond to the optimal alignment of energy levels for each transition. Also, it is demonstrated that asymmetric gain profile in design with two optical transitions can be the cause of self-starting harmonic combo emission in terahertz quantum cascade lasers. Moreover, in our lab, we have observed dual lasing channel effect in QCLs, even when we did not expect to see that. And here you can see emission spectra of QCL based on conventional resonant phonon design with maximum gain around 4 terahertz. And you see that there are two main modes separated by more than 200 gigahertz, which is significantly larger than mode spacing of Fabry-Perot modes with 1 millimeter cavity length. So we suppose that this behavior can be related to the presence of dual lasing channel in this laser. The other laser has two families of Fabry-Perot modes around 3.3 and 3.9 terahertz, which we associate with two optical transitions in active model due to the presence of two upper laser level, as you can see here on this band diagram. So, in my opinion, terahertz quantum cascade lasers is a perfect platform for multi-channel generation and also for two-photon design realization. And here you can see our proposal of 5-level laser scheme for two-photon emission. This is achieved by implementation of an additional laser level to the conventional four-level scheme with resonant phonon design. So in our proposal, electrons pass through an additional laser level, which is the low laser level for the first radiation transition and the upper laser level for the second one. So in this scheme, we can observe the following sequence: resonant tunneling, emission of the first photon, emission of the second photon, and relaxation by resonant phonon process. It is easy to see that to have an optimal level alignment in two-photon scheme, we need to apply high electric field, which demands high operating voltages for the energy of one photon. An advantage of two-photon scheme is a much weaker gain saturation effect under the increase of photon density in a laser cavity. So just using the simple model of rate equations, it is easy to see that the nonlinear parameter alpha, which is included in the resulting gain, is 2 times smaller for the two-photon design in comparison to the one-photon scheme. So this leads to significantly slow saturation of the resulting gain for the two-photon scheme. And here you can see how the gain depends on photon density for one and for two-photon schemes. So using two-photon schemes makes it possible to achieve significantly higher photon densities, which should potentially increase the radiation power of laser. On this slide, there is a resonant two-photon design with 4 quantum wells in active model, which we have developed on the basis of two-photon laser scheme. Due to the extremely low energy of terahertz photons, we have used a standard material system, gallium arsenide, aluminum gallium arsenide, with 15% of aluminum in barrier layers. And I would like to point out that we choose the maximum gain around 3.75 terahertz as a target frequency for this design. And the first attempt of an experimental realization of two-photon design was made with molecular beam epitaxy growth technique. And there were grown two structures with numbers 665 and 669. And here you can see X-ray diffraction curves of the grown structure, heterostructures, which have relatively high deviation of period, of actual period from the nominal period. However, even in the case of structure 665 with minus 5.5% of deviation, the laser threshold was achieved, and the signal of this laser was quite small, but it was still enough to measure a cyclotron resonance. And this experiment has helped us to measure roughly the generation frequency, which is equal to 3.8 terahertz, and coincides good with calculated gain spectra. On the basis of structure 669, with smaller deviation, the signal was quite well, and the emission spectra of this laser were measured by Fourier transform spectrometer. And here you can see the spectra of TeraGers QCL with a maximum intensity near 3.8 terahertz, so the same as the previous structure. But we could measure spectra only up to temperatures of 30 Kelvin, as at high temperatures the laser signal become very low, and we associate such low temperature operation with the problem of doping this structure. It leads to significantly high operating voltages, more than 40 volts, as you can see on the current voltage characteristics. Another attempt of experimental realization of two-photon design was made with alternative epitaxial technique, metal-organic vapor phase epitaxy. I need to say that it is non-trivial method for growth of TeraGers quantum cascade laser structures. And as far as I know, before us, only one laboratory headed by Eli Capone from EPFL demonstrated a successful growth of TeraGers QCL by this method. So during a MOVP growth of two-photon TeraGers QCLs, we have made only one campaign with two growths, and each growth gives us 3 laser structures. To improve the abruptness of semiconductor interfaces, we use so-called low-pressure MOVP growth with low growth rates comparable to molecular beam epitaxy. And so such growth rates allowed us to achieve sharp interfaces, as you can see it on the transmission electron microscopy image. Moreover, we have used XRD measurement to characterize the quality of grown structure. And finally, we choose two structures for TeraGers QCL fabrication. And here you can see a photo of fabricated TeraGers QCL with double metal waveguide. The typical width of waveguide is about 100 micrometers, and the waveguide length is in the range from 1 to 3 millimeters. And I need to say that we were lucky to get laser generation from both the first and the second growth. On this slide, you may see the light current voltage characteristics of TeraGers QCL based on the first growth structure. We observed the simulated emission with current above 2 ampere in a laser with 1 millimeter cavity length. And we suggest that such high current densities are related to a high level of background doping in the MOVP reactor. And to measure the emission spectra, we choose 4 bias points on the light current characteristics of the laser with 2 millimeter cavity length. And here you can see the measured emission spectra for each bias point with spectral lines which are very close to the target frequency of two-photon design. Here you can see the measured emission spectra at different temperatures up to 16 Kelvin and 1 bias point which correspond to 6 ampere injection current. And the maximum operation temperature of this laser is about 70 Kelvin, and the total bandwidth is about 100 gigahertz. And also we notice an unusual behavior of splitting the most intensive line into 2 lines with spacing of 5 gigahertz. Actually, we still do not understand the nature of such behavior, but such splitting effect we observe only in two-photon QCLs. On this slide, you can see a good agreement between the emission spectra of TeraGers QCL grown by molecular beam epitaxy and metal organic vapor phase epitaxy. So in other words, QCLs based on heterostructures grown by two different epitaxial methods demonstrate a very similar lasing around 3.8 terahertz. And probably such stability can be associated with high tolerance of the developed two-photon design to the deviation of period thicknesses. The laser based on the second MUP growth structure demonstrates a lot of interesting effects. At first, the given laser demonstrates high operation temperatures, more than 100 Kelvin, and then, as you can see here, the light current curves have two peaks, which are very similar to laser with dual lasing channel. This can mean some non-resonant generation of two photons. Moreover, the central frequency of this laser shifts to 3.6, 3.7 terahertz with an interesting comb effect at high injection current. Also, this laser has a significantly larger generation bandwidth, which is equal to 400 gigahertz, and there are several spectral modes with a mode spacing from 100 to 200 gigahertz. And this behavior can be associated with different energy of the first and the second photons, and consequently with some asymmetric gain profile. And moreover, we have found out a significant change in integration intensity of this laser during the pulse. Here you can see the light current curves, which were measured in different parts of 2 microsecond pulse. And you can see that both curves fall and rise sharply. And to understand such laser dynamics, we decided to measure the time dependence of emission spectra. And here you can see some kind of a map which describes a time dependence of mode generation. And it is easy to see that the generation of high frequency mode occurs with a 1 microsecond delay. So such temporal evolution of mode generation can be explained by the different times of photon activation. For example, at the initial moment of the pulse, the second photon is emitted between level 4 and level 3, and this process leads to a decrease of electron population in level 4 and increase of the population inversion between level 5 and level 4. So this can be a reason for the delay of the first photon emission. So to sum up, we have proposed to use two-photon laser scheme in a gain media of terahertz QCLs, and on the basis of this scheme, we have developed two-photon design with maximum gain around 3.75 terahertz, and terahertz QCLs grown by molecular beam epitaxy and metal organic vapor phase epitaxy demonstrate emission in the range of 3.6, 3.8 terahertz with maximum operation temperature around 100 Kelvin. And also we find an interesting effect. We have observed the temporal evolution of mode generation, which can be associated with the two-photon nature of these lasers. So thank you for your attention.
Thank you very much for your talk, which is very rich with the basic of laser physics. The talk is open for discussion, for questions. If you could show these energy diagrams, which illustrate the generation, schematic.
Okay, this one?
No, not this one. Just the principal one with the energy levels. So we are talking here of the true two-photon design, which means that the quanta on the right are equal to each other, and the transition is coming through the virtual level. Yeah, right?
Yeah, that's right. That's right.
But
So
finally, you showed us the same diagram with the different energies of photons.
So
H omega 1.
So we suppose, we suppose that maybe due to some inaccuracy during the growth, these two transitions can be not equal of energy. So it can be due to some problem in epitaxy. It's like we try to describe the effect which we see experimentally.
But in
we suppose that.
Yeah.
So in principle, when we develop this design, we try to do that these two these two transition is equal by energy, but experimentally the situation may be changed.
But why is the reason? Why it should be different? I cannot imagine anything.
Due to the problem, due to epitaxial problem, we need so we have for all of our structure we have significantly high deviation deviation of the period from nominal period. So if the thicknesses of the layers in Q cells is different, so you can get any energies of between these levels.
So it's a sort of inverted phenomena of some frequency generation. Okay.
Can you repeat?
Did you ever try this structure in the amplification mode? I think it will be immediately clear. Is it a true to photon or cascade process?
No. Unfortunately, not yet. So it's a good idea to try to amplificate by this structure some radiation.
In this case, you will obtain a very sharp dependence on the level of pumping. It should be very non-linear, quadratic approximately.
Yeah. Thank you for
thank you very much. Some more questions, please. No question. Thank you very much again for the very interesting talk, for the very fundamental.
Thank you.
Yeah. So this part of our section is over. We have lunch. So we will meet here after it. Thank you for your attention.
Dear colleagues, we start the next session of laser matter interaction, and the first report is holographic security science based on LIPSS physics and technology. Reporter Dr. Galina Одинцова, ITMO University, St. Petersburg, Russia.
Okay, dear colleagues, it's an honor for me to make a presentation at this conference. And today I want to tell you about holographic security labels based on LIPS. And I think that all you know what is LIPS. And we can get a LIPS on almost all materials. And LIPS is a polarized dependence structure. And LIPS has been studied since 1965 years and continues to be studied to this day. And every year we have a lot of paper connection with LIPS. And you know a lot of potential application of LIPS. We can control optical and mechanical properties. We can control wettability. And, for example, biological application to control cell adhesion and cell behavior. But for me, I don't know the real valid application of LIPS. Maybe you know. And it's some strange, because LIPS is a refractive diffraction grating as protective rainbow hologram. And it's look like same. And why? We don't have real applications. I think that it connects that all applications, we try to get a highly ordered LIPS, like that. And we don't like irregular LIPS. We think that it's not good. Because we have a bifurcation on the grating, and it's a stochastic process, and I don't know why, but we don't like it. And what do you think? Are irregular LIPS useful or not? And for me, I think that irregular LIPS useful. And please remember fingerprint and compare it with laser beam print with LIPS. I think it's very similar and also stochastic. And if we can control laser beam print, we can create a non-clonable security tag. But how can we control bifurcation of LIPS? It's some difficult question. And for the first step, we choose a parameter LIPS, what we want to control. It's a period, depth, number of bifurcation points, and we choose two parameters with colleagues from the Institute of Automation and Electrometry, dispersion of LIPS orientation angle, and parallelism. You can see more detail. And we have a parameters. Schematic diagram of the LIPS recording setup is demonstrated on the slide. And it's important that we rotate half and quarter wave plates for change polarization from linear to circular, and to change to control of direction of linear polarization. And what we have? We have a LIPS with period about 1 micrometer, with height from 10 to 150 nanometer. And you can see the parametric gap for the formation of the most regular lips. It's a green color. And we estimate the temperature of lips formation, and it's before evaporation temperature. And after, we study influence of different laser parameters on structural features of lips. Glow parameter, parallelism parameters, period, and bifurcation point. And what we see, with the increase of power density, all the parameters grow, and the structure becomes irregular. And why? Due to the temperature gradient and the physics of remembering structure when we use scanning mode. After, we see effect of laser radiation ellipticity on regularity of lips. And you can see that when the ellipticity changes from linear to circular, irregularity of the lips increases, and due to the change in the direction of the interference field rotation. So we have a map, and for every laser parameter, we know all lips parameters, and we can control it. But what interesting? For example, we have one mode and 8 experiments with this mode. We have the same laser parameters, we have the same lip structure, but the location of bifurcation points in space is unique, like a fingerprint. And we can use this for create physical unclonable security tag. And we can control it, but can we create a real rainbow hologram by lips, like that? Yes? And the next, our task was, will they create a rainbow hologram by lips. And please remember security holograms from CRIP10. And you see various dynamic effects. And our task was try to recreate some of them on steel. And the first step, we record color coordinates under various lighting conditions. For that, we use a special device, and we have a color map. After the second step, we select of effects for every area. And now I show you our effect. The first, you see the physical unclonable security tag. The second, kinegram, pseudomotion of lines, pseudomotion on circles, it's our examples, pseudomotion of images, you can see horse. And we can switch image, for example, from sun to moon. And we can create a volume effect. And we choose what we want. But how can we create it? And the third step, record of the desired effect with given colorimetric coordinates. For example, we want to get image switching effect. And we want to get 2 QR codes with different reading angles. And we create pixels consisting of 4 areas. 2 parts of pixels, it's for 1 code. Third part for 2 code, and 4 part for the physical unclonable security tag. And in this case, we see 2 records from different sites. The second, we want to get a kinegram and pseudomotion of lines. You see movement of lines. And how can we do it? And if we will change orientation of lips continuous, we will have a line movement. And how can we control orientation of lips? we can continuously rotate half wave plate. And using that, we get a pseudo-motion of lines, you can see. Also, we can get a pseudo-motion of images. You can see bird. And, for example, switching effect, it's a different image. If it will be interesting after, I can tell about it more detail. And volume effect. You can see in structure, with our pixel have a different structure for volume effect. And last step, it's necessary reading of the tag and writing to the database for authentication. For example, we have a label. After we identificate it, and definition dynamic effect and characteristics of unclonable security tag, period, number of branch points, DLO, and parallelism. And write it to database. And after, in any moment, we can check, fake it or an original label, out identification, this label. And as conclusion, we choose, or we developed a single-step method. It's very important that single step for recording security hologram on metal. Now we demonstrate it on stainless steel, but I think that it will be interesting on nickel or maybe on another materials. And it's very important that for every effect we use only one equipment. The performance of the method is 2 square centimeters per minute. And we can create different visual effects and also physical unclonable security tag. And we developed a model for industrial produced equipment Minimarket 2 for realize this technology. And in conclusion, I want to present our team of Institute Laser Technology. We research different fields, and we have another project, it's only one from them. And thank you for your time.
Thank you, reporter, for very interesting report. And any questions, please?
Какой?
12. Вот это вот число вот этих вот разветвлений, да?
Да, bifurcation point.
Да, бифуркации вот этих. Как? Вот...
Bifurcation point.
Ну, я понял, да. Ну, как вы их что-то контролируете, они где попало же попадают?
Okay. Now I open this slide.
Да, вот это 12, по-моему.
Yes.
Вот это вот левое.
I think that this picture is best. You can see number of a bifurcation point and ellipticity. And for every ellipticity, we have a number of bifurcation points. But location of these points is different. And we can control number, but location we cannot not control. Yes, and therefore we have a unclonable. Yes, it's interesting, I think. We can control it, but we cannot control it from another side.
Next question.
Do you protect your ellipsoid layers on surface?
With additional layer, with additional cover?
Yes.
No.
But if I take it with my finger, I destroy this?
You don't destroy it, but maybe if we will have a problem with reading, we can, не знаю, как это, протереть с помощью спиртика. Да, yes, we have a good save. And we have a test, if it's interesting, I can show you about mechanical, chemical, and temperature resistance for lips. And it's normal, it's the same on holographic, rainbow hologram on in other products.
Thank you.
Other questions? Not questions. Thanks, speaker, again, please.
Thank you.
And next, a report from Ural Federal University, Professor Vladimir Shur, light frequency conversion by periodically pulled ferroelectrics.
It's a great pleasure to be here, and to tell about our many years, activity with production of light frequency conversion in periodically pulled ferroelectric crystals. It's possible for us to prepare the domain structure, and this domain structure allows us to change the frequency of the light frequency, and people ask me what frequency from any to any. Really, it's quite a wide activities. It's several groups of people from different places. You can see from Novosibirsk and Ural Federal University. Well, so the idea of preparation of such periodical structure appears more than 50 years ago. And it had been done by a group of Nobel Prize owner Blombergen, who have Nicholas Blombergen, and the idea was to prepare some, crystals, the small plates of the crystals, but in short time it appears some ideas that it's possible to realize it by ferroelectric domains. But when people calculate, they find that really the period must be about few microns. But reproducibility of the period must be about 10 to 20 nanometers. And for that time, and for tens of years, it was practically impossible to produce something like this. Nevertheless, just now, it's quite reasonable. It's possible to do it. So this is the parameters. It's possible to get any kind of, frequency transformation. In this case, it's typical lengths of crystals, width, thickness. It's possible to have the second harmonic generation, and the only limits in this case is the transparency of the crystals. So typically for lithium niobate and another oxide crystals, it's from about 400 nanometers to about 4.5 microns. Also, it's possible to have optical parametric oscillation. In this case, it's also quite exciting results can be done. It's possible to do generation and measurement on terahertz and the difference in some frequencies generation. So immediately it appears some problem. This problem to produce such a structure, and the idea is like a area of activity of science and application, so-called domain engineering. So it's creation of some stable domain structures. They don't change during the application. Very important point in commercially available ferroelectrics. Because for the first time when I come to this society and try to speak about some other crystals, they told that this one is the most important. And in this case, it's possible to improve many characteristics. I will speak today only about one of them, about optical characteristics, but it's possible to do also piezoelectric, and some other. It's possible to produce it in bulk crystals, in waveguide devices, and it's not, in this case we use nonlinear optical crystals, but many of ferroelectrics just nonlinear optical crystals, good nonlinear optical crystals. So it's possible to do is periodically pulled lithium niobate, the most famous lithium tantalate, KTP, KTA. Domain periods it's just in this, you see, region from 30 to 4 microns. Yeah, the problem, nevertheless, it exists some problems how to achieve submicron domain periods, and I will show some results in this area. And really, it's possible to tell that we work with domain engineering with nanoscale period reproducibility. So reproducibility, in this case, it's become really nanotechnology. So this is the first very famous paper when people for the first time applying the voltage to the electrodes and produce the structure. It was some secret of this paper. So people for a long time can't apply the high NAP field. And these people use the thin sample, but not write about it. So it was not good for application, but the thickness was only 200ths of microns. It's very interesting to tell you that in few months, in 5 different labs over the world, people obtain the results in ½ millimeter. Yeah, it's such a psychology which appears sometimes in science. You can see very famous history. So just now it's possible to produce, it's lithography for the first time, then domain engineering, which differs for different materials, different periods and so on, processing, optical testing, and so on. As a result, you produce, and so the most typical is application of electric pulses to specially organized periodical electrode structure. As a result, it's possible to have a second harmonic generation. This is the most classical material, lithium niobate doped by magnesium oxide, which people used. It's possible to see that the quality of the structure can be produced very high quality. This is cross-section. You can see from the top to the bottom in 1 millimeter thick sample. Even when the period is about 4 microns, it's possible to have practically ideal structure. Yeah, this is also a good test which demonstrates that the temperature dependence of efficiency is just as predicted by theory. So another material which appears just now and people use it is lithium tantalate, and especially stoichiometric lithium tantalate. It's a very unique material, not so easy to grow it, so only one place in the world can do it on a good level. Yeah, but nevertheless, it's possible to use lithium tantalate, also congruent material doped and obtained also good structures, very uniform. You can see this high uniformity. Yeah, and as a result, it's possible to obtain the output second harmonic generation above 50 watts, speaking about CW. Yeah, this is just demonstration how it looks like, this dependencies of the power. Yeah, and this is different materials which can be done, which can be produced. Yeah, you can see really it's possible to produce any. Yeah, it's only just what people ask us about. And the average energy just now for CW is about 20 watts. But it's very important to take in mind that really for conversion efficiency for pulse lasers, about 70%, even in 1 centimeter length crystal, and what's important, without cavity, out of cavity. So it's absolutely unique efficiency, and this technique is the only which allows to have such a. This is some demonstration. It's some model, see our crystal with all devices. You see, which have done in collaboration with, you see, Irepolis, IPG. Yeah, and just now it appears even some, you see, devices. They produce some devices with such elements, with such periodically pulled crystals, and various applications of it. Another important point, it's possible to have optical parametric oscillation, and in this case it's possible to do something in near infrared. And one very unique situation which can be realized, it's possible to prepare so-called fan-out structure. You can see the geometry here. And when you move see the beam on the structure, it's possible to change the period and the change of the wavelengths. And it's possible to change the wavelengths, you can see here, from 2.8 to 4.5. Yeah, absolutely unique situation, you see, which can be done. And you can see that efficiency is also not bad. It's about 15 or 20% in this area. Yeah, so it's possible also to produce a structure. It's one is important point that really the thickness can be, in this case, up to 3 millimeters. It's close to world records in this case. Yeah, then it's possible to have optical parametric oscillation in KTP and KTA crystals. These crystals looks very nice because symmetry is just good for stripes. Yeah, and it's possible to organize very nice stripes. And as a result, it's possible to have very good structures. And to realize switching, you can see here the wavelengths 2.3 microns. It's possible to have also 3.4 microns. And the quantum efficiency is close to 30%. It's possible to use different technique, yeah, more exotic. For example, electron beam, and we have done it also. It's possible to realize it by, you see, electron microscope, with scanning electron microscope, with special device with it. And as a result, it's some secret in this, yes, not secret, but some special property. It's necessary to cover the surface by resist, you see, electron resist. And in this case, we was the first in the world who have realized this one. It was the first publication. It's a structure on both sides of 1 millimeter thick sample, and you can see it's just same on both sides. So it's absolutely vertical walls. Yeah, and it was a really wonder because nobody have done nothing like this. So it's possible to produce it also. It's possible to use the scanning tip, yeah. Of course, the first thing which people do is just some drawings. You can see some nice drawing. It's very important that being a very good resolution, nevertheless absolutely stable. Yeah, but it's possible to do something more serious. And what we do now, quite recently, is just some works with lithium niobate thin films, which is produced by ion slicing. Yeah, it's preparation of some wafer, implantation by helium ions. Then it's possible to have deposition of silicon on another wafer. Then they got together, some bonding. And as a result, is you see some crack along 1 millimeter from the surface. You see, so one micron from the surface. As a result, it's possible to produce some crystal. It's lithium niobate on isolator. And in this case, it's possible to use it, really various applications, a lot of publications now about it. And Chinese company who produces very successfully. We collaborate with this company. It's possible to have it Z-cut, so perpendicular to PolarX, Z-cut with the electric layer, with bottom electrode, and also perpendicular, so various crystals can be used. But the most important point is the thickness of the layer is about 700 nanometers and 400 nanometers. And the quality of the surface is extreme. So the roughness below 1 nanometer. So in this crystal, it's possible to realize the domain structure. This is periodic structure produced by bias tip of scanning probe microscope. And you can see here that the period about 150 nanometers have been observed. Period. So the sizes is even smaller. Yeah, it's possible to demonstrate that by voltage it's possible to control the period, the parameters, and it's possible to organize the structure in other direction. Yeah, and in this case it's possible on X-cut, and wedge-like domains can appear also quite regular. The most important point for this audience is that just now we do something with light-only switching, without any voltage, without any electric field. Yeah, it looks extremely interesting. So such a domain engineering is possible. The first one which we have done a lot of time is we use the infrared irradiation, pulse irradiation. And this pulse irradiation, 10 microns, gives us the area which is irradiated. And in this area it appears small domains. And the size of these domains is about 100 nanometers. Yeah, so it's stable structures. It was switching by pyroelectric field, and we have a deep study of this process. But in this case, it's a regular structure, but it's possible to produce also irregular structure. But in this case, it's necessary to use a femtosecond infrared laser for such domain engineering. This is the first results, which have been done by a group from a Krolikovsky group from Australia. Yeah, and they demonstrate that it's possible to produce such structures just by irradiated by femtosecond laser. The most important point is that in this case it appears a new stage in domain engineering. It was possible to produce domains in the bulk, completely in the bulk, not coming out. It was absolutely impossible to do by any other method. You can see here, yeah, such structures. Yeah, this is also a demonstration, and it's possible to produce in many crystals. Yeah, it's possible to do it in lithium niobate, tantalite, and many others. Yeah, not so many crystals people have done because a few of groups in the world work with it. And we, between them, just now we have obtained such structures. And the last one, yeah, it's possible to produce also the waveguides by femtosecond laser in the bulk. Yeah, this gives us the chance to have such a structure. You see this cross-section of the structure, you can see how it looks like. And really it's possible to have this structure just in periodically fault crystal. Yeah, so you have also transformation and the structure, you see, which is in the bulk. Yeah, it looks extremely promising, very interesting, and very new product. Yeah. That's all. Of course, you understand that it is also the main structure, and I hope that it will be lived with you forever. Thank you.
Okay. Thank you very much for amazing talk, I think. Yes, and maybe it's for plenary session. Very interesting. Okay, do you have any questions?
Вот можно это для пешеходов? Я вот вообще не понял, откуда вот, как она вообще вот работает? Ну, было омега, а стало омега пополам. Вот эти полоски сделали, и что?
Yeah, so really the situation is as follows. Yeah. So when you use the crystal without any domains, in this case also you will have the second harmonic generation, but intensity will be higher, lower, higher, lower. Yeah, so such a modulation, and you can't have bigger one. It's necessary to use the phase matching. So the phase matching is necessary to choose the direction in the crystal when you see two lights, which appears, you see two components, will have the same velocity, the same coefficient, you see. In this case, but in this direction, the nonlinear optical coefficient is low. Yeah, and it was idea of Blombergen, that it's possible to have thin crystals, and when it's come to the top, then he give here another crystal which is rotated. So another orientation, and it will continue to grow. Continue, and so on. Yes, so as a result, but in this case, it's possible to use the direction with maximum value of nonlinear optical coefficient. And it gives you extremely high values which can't be produced. Of course, at the beginning, people understand that it's very difficult, practically impossible to produce such a, you see, it was necessary to have the hundreds, thousands of them. Yeah, but when they speak about domains, it looks reasonable, but not in short time. It's needed several tens of years to realize it. Just now it's a product and it's possible to realize it quite easily.
Okay, thank you.
In this case, the period allows you to prepare it for any wavelengths. So
I think
it
that
depends
in Clore
just
you
on
can
period.
continue. After, okay. Sergey?
Thank you, Vladimir. The results, the achievements in this domain is really impressive. I would like to ask you about electron beam variety of this method. And you mentioned that you use photoresist on top. Does it mean that you use space charge to initiate?
I can tell there's a problem, yeah. So at the very beginning, people understand that it's very easy to have very small spot by electrons, yeah. But another problem, that the spot immediately separated on the surface. So you can't localize it. But when you have the photoresist, you localize it in photoresist.
Yeah, you have.
And in this case, it's necessary to be very careful. Yeah, when you come it's necessary to produce such a tip of electrons which just touch the surface. When you change it, so in this case, it's necessary. We are not people who discover the method, but we are the only who give the possibility to have a good structure.
Yeah, it makes the process more deterministic.
Yes,
and,
yes.
Less stochastic.
Yeah.
Thank you very much.
Okay, any questions? Okay, thank you very much. The next speaker is Professor Stanislav Shendarov from Tom State University. Can we change presentation, please? Okay, thank you.
Dear colleagues, my report, photovoltaic tweezers on the base of diffusion structures, lithium niobate doped by copper. From our group, Tomsk State University of Control System and Radioelectronics. What is photovoltaic tweezers? In the photovoltaic crystals, such lithium niobate, the illumination by homogeneous light induced the redistribution of charge carriers, and strong electric field generate in such crystals, and you can see here the evanescent field above the surface of the crystals, and due to dielectrophoretic force, it is possible to manipulation of ensemble of particle. And advantage of photovoltaic tweezers is the possibility to repeat it using of monocrystal substrate, as well as minimization of overheating for captured objects, and very small paper as a rule by a group of Mercedes Carrascosa about this problem, and to geometry used for such systems. Parallel geometry for X-cut of crystals, and perpendicular geometry for Z-cut of crystals, and to use such photovoltaic materials, the concentration of trap centers. In the case of lithium niobate doped by iron, it is iron 3 plus, and traps iron 2 plus. In the case of high concentration of such impurities, the strong electric field can be generated in such substrate, about 100 kilowatt per centimeter. And to configuration used for manipulation of such particle, nanoparticle, it is volume variant and waveguide variant. In this case, lithium niobate crystals doped by iron usually used. And electric field repeated the distribution of light intensity in the crystals, and such high electric field due to the electrophoretic forces aggregate the nanoparticle, and pattern of such nanoparticle repeated the electric field distribution. And such method can be used for biologic object also. And not only iron can be used for photovoltaic impurities, but also we create the diffusion structure of lithium niobate doped by copper. And in this case, also we observed aggregation of nanoparticle. And in this report, we present the results of experimental realization of the technology of diffusion doping of X and Z congruent lithium niobate crystals by copper, as the result of studying their photorefractive and photovoltaic properties. And relating diffusion of kappa into lithium niobate substrate is a very interesting result. First of them, the diffusion of copper not inhomogeneous only 20%, but other paper the inhomogeneous very high, and in case of impurities copper pulse and copper 2 pulse donors and traps, the concentration of such impurities can be equal to 0 at boundaries of the crystals. But to realize the photovoltaic tweezers, we can use the structures with high concentration of such impurities. And in our experiment, we create two substrate doped by copper. First of them is for XCAD lithium niobate crystals. We used the temperature diffusion 1000 Celsius degree, and after diffusion, the substrate was created on two samples with widget area, and we study the transmission coefficient of such sample. And you can see here two dependencies for transmission coefficient point experimental date and solid curves theoretical consideration. And we used two laser beam with wavelengths of 532 nanometer and 808 nanometer for analysis of distribution for copper pulse donor and copper 2 pulse traps. And there is theoretical model to Gaussian function for distribution of optical absorption. And there is two dependencies of concentration on the depth in the sampler to Gaussian function, and for trap concentration of traps on the boundary of crystals is very small. And other samples was the Z-cut lithium niobate crystals, and in this case we deposit the film, metallic film of copper on the two face of the crystals, and after diffusion at 600 Celsius degree, we study the transmission dependency on the depth along the Z coordinate in the crystals. And we obtain the following distribution of concentration for donors for traps. It is very high on the boundary of the crystal, but in the perpendicular configuration, the high magnitudes of evanescent field not be obtained. And for study for the refractive properties, we use the experimental setup with two laser. One laser is used for reading volume holograms in the sampler, and second one for red laser for break diffraction to control of efficiency diffraction grating. And we study the diffraction efficiency that depends from time for initial part of this process, and for measured angular selectivity for such photorefractive grating. And point is experimental date and solid curves. It is theoretical model. And we estimate from our experimental date certain parameters of investigated X cut lithium niobate diffusion structure doped by copper. First, we estimate the glass constant photovoltaic properties that characterize it. It is equal to 8 picometer per volt. And we modified the model of distribution for donor and for traps by additionally taking into account the constant value of these impurities in the crystals. And there is my conclusion. The technology of copper diffusion into X-cut lithium niobate substrate is not trivial and requires detailed study. Thank you for your attention.
Okay. Thank you for your talk. Do you have any questions? Okay.
Thank you for the talk. Maybe I missed, what is the reason for this inhomogeneous distribution of copper after your diffusion? So I thought it's not the simple exponent or error function or some multi-peak distribution. What is the mechanism?
It is very not answer for this. And we
yes.
In first experiment we create the structure with Gaussian profile, but in the other experiment don't create.
So it was not reproducible, yes?
No, not.
Okay,
not.
I see.
And
Thank you.
I believe we can must control temperature, diffusion, time of diffusion, the thickness of the copper film, and other parameters.
Okay, thank you.
Okay, we have time for one question. Yes? Yet? Nobody? Okay, thank you very much. The next speaker is Anton Burtsev from Institute of Laser and Information Technology of Russian Academy of Science. And please, can we change presentation? We are waiting presentation. Thank you.
Dear colleagues, my name is Anton Burtsev. I am researcher of Institute on Laser and Informational Technology of Russian Academy of Science, and I will submit to you this report about phase change materials and their applications in devices. Unfortunately, our supervisor, Andrei Anatolyevich Lotin, can't submit this report personal, and I will say a few words about our research. First of all, what is the phase change materials? Phase change materials have two or more discrete phase states with different properties. Usually, we see amorphous and one or more crystalline phases. The most popular phase change materials are tellurides, especially JST, germanium, stibum, tellurium, and phase tradition are induced by thermal excitation, usually optical or electrical pulses, and for crystallization process we use intermediate laser or electrical pulse. The material is heated above his temperature crystallization, and we have the material became crystalline. And for amorphization, we must heat the material about its melting point, and the amorphization is the process of melt quenching or glassing in Russia with high cooling rate. A few words about our experiments. We research thin film samples of JST and on quartz glass substrate, and they're produced by vacuum thermal deposition. Phase transition were induced by laser pulses. We use two lasers with nanoseconds and femtosecond pulse duration. And we use pump probe scheme, and we can see as change in optical parameters, reflectivity and transmittivity coefficients. On this slide, we see experiments and modeling of phase transition in JST thin films induced by nanosecond laser pulses. We see as changes of reflectivity and transmittivity coefficients, and see that the simulated model and it describes phase transition and by the layer to layer and based on heat equations and the classical Stefan problem. And right we see XRD structures researching, and we see that with phase transition and JST become between amorphous and low temperature metastable cubic phase centers or rock salt. And what we can see when we used femtosecond laser pulses, we see that the two temporal sections a very strong sharp in the sub nanosecond, and and local crystallization. And there are many different research says about the first attempt, the first sub-nanosecond sharp. Some say that it can be explained, but photo and induced carriers, and it's to temperature model that electron heating and from heating electron we see phase transition by heating the lattice atoms, but some researcher tells that it can be explained by only thermal effects. For example, the first we see fast reamorphous regulation of the amorphous phase and crystallization of reamorphous phase. And it's very difficult. So we must the most analysis is two of these effects, and photo-induced carriers and the very very complex crystallizations. We say structure evolution crystallization, and we describe but change of Raman spectra and XRD diagrams. And XRD diagrams we see of JST we see not only rock salt structure cubic, but and another for primitive or simple cubic phase too. A few words about new materials as gallium tellurium. It's a new material. This is a new material, and in experiments we and our colleagues see that this material has a phase-centered cubic phase too, but it isn't stable and can be. It can be used only for very fast transition, very fast transitions. And that we see the discrete thermokinetic computational model for describe of processes of crystallization and amorphization. We used this new model because another simulations based, for example, on Stefan problem as we do, or Kolmogorov or Kolmogorov-Avrami are not effective for phase transition in thin films and ultra thin films. So we used the model based on classical nucleation theory, and we see that nucleation and crystal growth are independent and are independent. It describe independent in our model, and we want to verify this model for femtosecond and nanosecond pulses. We used transmittivity electron microscopy images and our model. It's very effective for describe crystallizations and amorphizations by nanosecond pulses, but have some problems with femtosecond pulses, and we understand that for femtosecond laser pulses we must use some some solution for first principles or two temperature model with electron excitations and we transport energy from electrons to atom lattice. And a few words about modern memory devices. Stanford Avshinsky noticed in the beginning of the century that phase change materials and memory devices has some properties. It is like narrow-inspired systems, and he said about the threshold phase transition, cumulative and cumulative incubation pulse energy, and non-linear change of the physical properties in phase change. He said about reflectivity and resistivity. And it is a property of the materials, and we can think and realize some narrow-inspired devices based on these materials, and later it was developed, and architectures on planar photonics. We've got with phase change material, or cell, or layer, or the latest plasmonic antennas, and we can induce phase transition in materials, and we see as change the transmittivity of waveguide. And it was great, but the most systems are based on silica technology, and so we developed a biological synthesis prototype based on polymer waveguide with JST cell. And we see modulation of transmittivity, and can describe that it is by the mathematical model in COMSOL software. Thank you for your attention, and if you have questions.
Okay, thank you for interesting talk. Do you have any questions? No, I have. Oh, okay, we forgot. Okay, please. Okay, do you have any questions? Okay, questions from me. Maybe you can answer, maybe not. When we create an artificial element, look like a human brain, what do you think? Can you?
Very, very good and very important questions, because some artificial neural network based on phase materials were created and based by PCRAM. And based on optics. The synapses used the planar waveguide with cell of JST, and for artificial neurons, usually based on ring resonator with JST cell, or Mach-centered interferometer with JST, and it's work in reality.
Okay, thank you.
Thank you very much for a nice talk. I would like to ask you, what is the cytotoxicity of your plates when you combine with neurons? Cytotoxicity, did you measure it?
Toxicity for human brains?
Yes.
I think that these materials are not very toxicity.
But you didn't measure cytotoxicity?
No.
No, okay, thank you.
Okay. Do you have any question? We have time for one. No? Okay, thank you very much.
Thank you for attention.
Okay, our session is finished. Thank you.
Не произнесу фамилию, да, не знаю его. Он не выступил почему-то.
Да.
Я так поняла, что он даже расстроился, что он не выступил, и просила перенести на завтра и сообщить ему.
Хорошо, попробуем.
Надо не забыть. Очень просила. Я так понимаю, он дошел там до ребят, и когда я тут сидела, мне дали, что вот вообще
Мы
не
его
сказали.
звали, он не откликнулся. Да, не
В
до,
общем,
не во
он
время.
переживает.
Ясно, хорошо, попробуем.
Всё.
Спасибо. Спасибо большое, что помогли.